In the deepest future, when every star has burned out and every black hole has evaporated, a single proton drifts through space colder than anything you can imagine. This particle has outlived galaxies, survived the death of time itself, and now witnesses something no human mind was meant to see. You are about to journey through 14 billion years of cosmic history, past the death of our sun, beyond the collision of galaxies, and into the final moments when the universe reaches its ultimate temperature, absolute zero. We will explore dying stars that rain diamonds, black holes that devour entire solar systems, and the quantum mechanics that could erase reality itself. Please like and subscribe to join this journey to the edge of existence. Prepare yourselves. We begin. Step outside tonight and look up at the stars twinkling above you. Every single point of light you see is burning through fuel it can never replace, racing toward its own death at speeds that would terrify you if you truly understood what was happening. The star nearest to us, our sun, consumes 4 million tons of itself every second, converting matter into energy through nuclear fusion deep in its core. Think of it like a massive campfire that burns 4 million cars worth of material every heartbeat, and you start to grasp the violence happening 93 million miles above your head. But here is what makes this truly unsettling. The light hitting your eyes right now left most of these stars years, decades, or centuries ago. You are literally seeing the past deaths of suns that might have already exploded into supernovas, their final screams traveling through space toward Earth at 186,000 miles per second. The star Betelgeuse, visible as a red dot in the constellation Orion, could have detonated yesterday, and we would not know for another 548 years. Every star you see follows the same tragic pattern. They start as massive clouds of hydrogen gas that collapse under their own weight, heating up until nuclear fusion ignites in their cores. For millions or billions of years, they burn steadily, converting hydrogen into helium and releasing the energy that makes planets like Earth possible. But fusion creates heavier elements as waste products, and these heavier elements cannot fuel the nuclear fire. Iron builds up in the core like ash in a fireplace, and when enough iron accumulates, the fusion stops. When fusion stops, gravity wins. The star collapses in less than a second, then rebounds, in an explosion so violent it outshines entire galaxies. The explosion throws elements like carbon, oxygen, and nitrogen across space, seeding future planets with the materials needed for life. But the star itself dies, leaving behind either a dense neutron star or a black hole that will never shine again. Our sun faces a different but equally final fate. In about 5 billion years, it will exhaust its hydrogen fuel and begin burning helium instead. This will cause it to expand into a red giant star, so large it will swallow Mercury, Venus, and possibly Earth. Even if our planet survives the expansion, the sun's surface will be only 5 million miles away, turning Earth into a molten ball of rock with surface temperatures reaching 2,000 degrees Fahrenheit. The largest stars burn the brightest and die the fastest, lasting only a few million years before exploding. Smaller stars like our sun burn for billions of years, but they too must eventually fade. The smallest stars, called red dwarfs, burn so slowly they could theoretically last for trillions of years. But even these cosmic misers cannot escape the fundamental problem of stellar death. But compared to what comes next, individual stellar death looks almost gentle. The universe is already dying around you, and the process started the moment it began expanding 13.8 billion years ago. Every day, space itself grows larger, stretching the distance between galaxies and cooling the cosmic temperature by tiny fractions of a degree. This expansion acts like opening a window in a heated room during winter, slowly but inevitably letting all the warmth escape into the infinite cold of space. Right now, the average temperature of empty space measures negative 454 degrees Fahrenheit, just 2.7 degrees above absolute zero. This might seem impossibly cold, but it represents the leftover heat from the Big Bang itself, called the cosmic microwave background radiation. Think of it as the fading embers of the universe's birth, still glowing weakly after nearly 14 billion years. Every second that passes, this background temperature drops as space expands and the ancient heat spreads across ever larger volumes. You can actually detect this cosmic cooling in your own home. Turn on an old television set and tune it to static between channels. About 1% of that visual snow comes from the cosmic microwave background radiation, the dying heat of creation itself hitting your antenna. You are literally watching the universe cool down in real time, photon by photon. The expansion of space affects everything, not just temperature. Galaxies that appear close together today will drift apart over cosmic time, their light shifting toward red wavelengths as they recede from us. This redshift happens because space itself stretches the light waves as they travel, like stretching a spring until it snaps. Eventually, galaxies will move so far apart that their light will redshift completely out of the visible spectrum, making them invisible to any observers left in the cosmos. Dark energy accelerates this process, pushing galaxies apart faster than gravity can pull them together. Scientists discovered this acceleration only recently, and it shocked them because they expected the universe's expansion to slow down over time. Instead, the expansion speeds up, like a car whose gas pedal gets stuck to the floor. Dark energy makes up about 68% of everything in the universe, but we understand almost nothing about what it actually is or why it behaves this way. This accelerating expansion creates what cosmologists call the Great Freeze or heat death scenario. Unlike a big crunch where everything collapses back together, or a big rip where expansion tears apart atoms themselves, the Great Freeze allows the universe to expand and cool forever. Stars will eventually burn out, black holes will evaporate, and even protons will decay, leaving behind only elementary particles drifting through space at temperatures approaching absolute zero. The mathematics are inescapable. In a universe dominated by dark energy, entropy always increases and available energy always decreases. Every process that creates order, from star formation to biological evolution, happens by converting useful energy into waste heat that radiates away into space. Eventually, no temperature differences will exist anywhere in the cosmos, making it impossible for any work to be done or any life to exist. The cosmic microwave background currently glows at a temperature equivalent to -454 degrees Fahrenheit, but this will continue dropping as space expands. In a few billion years, this background radiation will cool below the temperature of liquid helium. In trillions of years, it will approach absolute zero itself. Yet even as this cosmic winter tightens its grip, some stars continue forming. Our sun appears stable and peaceful from Earth, but it hides a violent future that will destroy every living thing on our planet in exactly the way a serial killer might slowly poison a victim. The murder weapon already exists inside the sun's core, building up strength every second as hydrogen fuel slowly disappears and helium ash accumulates. In 5 billion years, this accumulation will trigger a transformation so dramatic it will turn our life-giving star into Earth's executioner. Here is how the murder will unfold. As the sun burns through its hydrogen fuel, the helium waste products settle in the core like sediment in a river. This helium cannot undergo fusion at the sun's current core temperature, so it just sits there, getting denser and hotter as more hydrogen burns around it. Think of it like pressure building up in a steam boiler with no release valve. Eventually, the pressure and temperature reach a critical point where helium fusion suddenly ignites in what astronomers call the helium flash. When helium fusion begins, the sun will start burning much hotter and brighter than it does today. The increased energy output will cause the sun's outer layers to expand dramatically, transforming it from a yellow dwarf star into a red giant hundreds of times larger than its current size. If you could somehow survive to witness this transformation, the sun would appear to grow from a small disk in the sky to a massive red orb covering 20 degrees of the horizon, roughly 40 times wider than the full moon appears today. The expanding sun will first swallow Mercury completely, vaporizing the innermost planet in a matter of days. Venus will disappear next, its thick atmosphere providing no protection against the approaching stellar furnace. Earth's fate depends on exactly how large the sun becomes during its red giant phase, but even the most optimistic scenarios spell doom for our planet. If Earth somehow avoids being swallowed entirely, it will experience surface temperatures exceeding 2,000 degrees Fahrenheit, hot enough to melt copper and boil away the oceans in minutes. The sun's surface during its red giant phase will sit only about 5 million miles from Earth, compared to the current 93 million mile distance. This brings the stellar surface closer to Earth than Mercury orbits today. Imagine standing on a planet where the sun fills half the sky with roiling, burning plasma, and you begin to understand the hellscape Earth will become. But the sun's murder of Earth will not be quick. The expansion into a red giant happens over millions of years, giving any surviving observers plenty of time to watch their world slowly cook. The oceans will boil away first, filling the atmosphere with superheated steam. The steam will then escape to space, leaving behind a dry, airless rock. Surface temperatures will continue rising until even the most heat-resistant materials begin to melt and flow like lava rivers. Any life that somehow survived the initial ocean boiling would face another killer: the sun's increased ultraviolet and X-ray radiation output. The red giant sun will strip away Earth's atmosphere entirely, exposing the surface to lethal doses of high-energy radiation. Even underground shelters would provide no protection against the relentless heat and radiation bombardment. The sun will remain in its red giant phase for about 1 billion years, plenty of time to thoroughly sterilize Earth and any neighboring planets. During this phase, it will lose about 30% of its total mass through powerful stellar winds. But this mass loss will not save Earth from incineration. When the sun finally exhausts its helium fuel, it will collapse into a white dwarf star about the size of Earth but with half the sun's current mass. The white dwarf will be incredibly hot initially, with surface temperatures exceeding 100,000 degrees Fahrenheit, but it will have no internal energy source left. Over trillions of years, it will slowly cool and fade, eventually becoming a cold, dark object called a black dwarf. But long before the sun reaches its white dwarf phase, something even more catastrophic awaits. Right now, across the universe, massive clouds of hydrogen gas collapse under their own gravity to form new stars at a rate of about 7 new suns every second. But this cosmic assembly line operates on borrowed time, and the shutdown date has already been calculated by astronomers who study the universe's inventory of star-making materials. In about 1 trillion years, the last star factory will close forever, leaving the cosmos to live off the stellar inventory already in stock. Star formation requires 2 essential ingredients: cold hydrogen gas and enough density for gravity to overcome the gas pressure trying to keep clouds expanded. Think of it like trying to squeeze a balloon until it pops, except the balloon fights back with gas pressure while gravity tries to compress it into a burning ball of nuclear fire. Early in the universe's history, hydrogen was abundant and cold, making star formation relatively easy. Entire galaxies blazed with the light of newly formed stars, creating what astronomers call the cosmic noon period about 10 billion years ago. But every new star removes hydrogen from the available supply, locking it up in nuclear fusion reactions that convert it into heavier elements. When massive stars explode as supernovas, they do return some material to space, but much of it consists of heavier elements like carbon, oxygen, and iron rather than the pure hydrogen needed for efficient star formation. It is like a factory that consumes raw materials faster than its waste products can be recycled back into useful inputs. The universe currently contains enough hydrogen to keep making new stars for about 1 trillion years, but the rate of star formation has already dropped dramatically from its peak. Today's universe produces new stars at only 3% of the rate seen during cosmic noon. This decline happens because most of the easily accessible hydrogen has already been used up, and what remains is either locked inside existing stars or spread so thinly through space that gravity cannot compress it effectively. Red dwarf stars accelerate this process by hoarding hydrogen for trillions of years. Unlike massive stars that burn bright and die young, red dwarfs consume their fuel so slowly that once hydrogen gets locked inside one, it stays there for longer than the current age of the universe. Think of red dwarfs as cosmic misers who never spend their money, removing hydrogen from circulation for geological ages. Galaxy mergers temporarily boost star formation by compressing gas clouds and triggering new stellar births, but these mergers become increasingly rare as the universe expands and galaxies drift apart. The upcoming collision between our Milky Way and the Andromeda Galaxy in about 4.5 billion years will create a brief burst of new star formation, but it represents one of the last major merger events our local region will experience. Dark energy makes the situation worse by accelerating the expansion of space itself. As galaxies move farther apart, they lose the ability to share gas and materials through gravitational interactions. Eventually, each galaxy becomes an isolated island in an expanding ocean of empty space, forced to rely entirely on its own dwindling supply of star-forming materials. The most massive stars, which burn hottest and brightest, will disappear first from the cosmic inventory. These stellar giants live for only a few million years before exploding as supernovas, so the universe will stop producing them within the next few billion years as the available hydrogen supply dwindles. Medium-sized stars like our Sun will continue forming for hundreds of billions of years, but they too will eventually become impossible to create. Red dwarf stars will be the last type to form, since they require the least amount of material and can ignite nuclear fusion even with relatively small amounts of hydrogen. But even red dwarf formation will eventually cease, as the remaining hydrogen becomes too diffuse for gravity to compress into stellar cores. When the last star forms in about 1 trillion years, it will likely be a small red dwarf in some remote corner of a galaxy far from Earth. This final stellar birth will mark the end of an era that began with the first stars only a few 100 million years after the Big Bang. After that moment, the universe will contain only the stars already burning, slowly consuming their fuel while no new replacements appear. But even before star formation ends completely, our galaxy faces a collision that will reshape everything. Deep in space, an invisible battle rages between two fundamental forces that will determine whether the universe ends in fire or ice. On one side stands gravity, trying to pull everything together into a final cosmic collapse called the Big Crunch. On the other side fights dark energy, pushing space itself to expand faster and faster until galaxies drift so far apart that the universe freezes into eternal darkness. This war has been going on for 13.8 billion years, and recent observations reveal which side is winning. Gravity appears weak compared to other forces, because you can easily lift a paperclip with a small magnet, overcoming the gravitational pull of the entire Earth. But gravity has one crucial advantage. It never stops working, and it affects everything in the universe simultaneously. Every proton, neutron, and electron pulls on every other particle across cosmic distances, creating an invisible web that tries to draw all matter together into increasingly dense clumps. In the early universe, gravity clearly dominated. Matter was packed so tightly together that gravitational attraction easily overcame the expansion of space, allowing gas clouds to collapse into the first stars and galaxies. Think of it like a tug-of-war where gravity had many more players on its side, easily pulling matter together despite space trying to stretch everything apart. This gravitational dominance lasted for about 7 billion years after the Big Bang. But dark energy grows stronger as the universe expands, while gravity grows weaker as matter spreads out over larger volumes. Dark energy acts like an invisible field that fills all of space and pushes against gravity's attractive force. The more space expands, the more dark energy comes into existence, creating a positive feedback loop that accelerates expansion even faster. It is like a tug-of-war where one side keeps adding new players, while the other side loses strength with every inch of rope that changes hands. About 6 billion years ago, dark energy finally overcame gravity's pull and began accelerating the expansion of the universe. This transition marked a turning point in cosmic history, shifting the universe's fate from potential collapse to inevitable heat death. Astronomers discovered this acceleration by studying distant supernovas and measuring how fast they were moving away from us compared to closer exploding stars. The mathematics of this cosmic war reveal dark energy's ultimate victory. Gravity follows an inverse square law, meaning its strength decreases rapidly with distance. Double the distance between two objects and gravity becomes 4 times weaker. But dark energy appears to have constant density throughout space. So as space expands and creates more volume, the total amount of dark energy increases proportionally. This creates what cosmologists call the runaway expansion scenario. As dark energy pushes galaxies apart, gravity becomes weaker because the matter is more spread out. Weaker gravity means less resistance to expansion, allowing dark energy to push even harder. The process feeds on itself like a chain reaction, with expansion accelerating exponentially over cosmic time. Current measurements suggest dark energy makes up about 68% of everything in the universe, compared to only 27% for dark matter and 5% for ordinary matter like stars and planets. These percentages mean dark energy has already won the war decisively. But the battlefield is so vast that the final consequences will take trillions of years to play out completely. In about 150 billion years, the accelerating expansion will carry distant galaxies beyond our cosmic horizon, making them disappear from view as their light can no longer reach us across the growing gulf of space. Eventually, only galaxies gravitationally bound to our local group will remain visible, creating the illusion that our small cluster represents the entire universe. The expansion will continue accelerating until even nearby galaxies drift out of sight, leaving behind isolated islands of matter separated by ever-growing oceans of empty space. In this scenario, gravity loses so completely that it cannot hold together anything larger than individual galaxy clusters. And eventually, even those will disperse into the cosmic void. Yet before this cosmic isolation becomes complete, our galaxy faces a massive collision that will temporarily defy the expansion. In about 4.5 billion years, our galaxy will experience what astronomers call a galactic train wreck when the Andromeda galaxy crashes into the Milky Way at a speed of 250,000 miles per hour. But this cosmic collision, rather than destroying everything, will actually extend the life of star formation in our region of space by billions of years, creating a temporary victory against the universe's march toward darkness. The collision between our galaxy and Andromeda represents one of the last great merger events that will occur in our local region of the universe. Andromeda contains roughly 1 trillion stars compared to our galaxy's 400 billion, making it significantly more massive than the Milky Way. Think of it as a massive freight train colliding with a smaller passenger train, except both trains are made of stars, gas, and dark matter spread across hundreds of thousands of light years. Despite the violent-sounding description, very few individual stars will actually collide during this galactic merger. The distances between stars are so vast that even when two galaxies interpenetrate completely, the probability of stellar collisions remains extremely low. It would be like firing 2 handfuls of sand at each other from opposite ends of a football stadium and expecting the individual grains to hit each other directly. Instead, the real drama happens to the gas clouds that float between the stars. As the two galaxies merge, their gravitational fields compress and heat these gas clouds, triggering an intense burst of new star formation called a starburst phase. The collision will squeeze gas clouds that have been floating peacefully through space for billions of years, compressing them beyond the threshold needed for gravitational collapse and stellar ignition. Computer simulations of the Andromeda collision predict it will create millions of new stars within the first few billion years after the merger begins. Some of these stars will be among the most massive ever formed in our cosmic neighborhood, burning bright blue and living fast before exploding as spectacular supernovas. The night sky during this period will blaze with newborn stars, making it appear as if the universe has suddenly become young again. The merger will also disrupt the supermassive black holes at the centers of both galaxies, sending them spiraling toward each other in a cosmic dance that will last for millions of years. When these black holes finally merge, they will release gravitational waves so powerful that they will ripple through the fabric of space-time itself, carrying away energy equivalent to the mass of several million suns, converted entirely into pure energy. This collision represents more than just a cosmic spectacle. By the time Andromeda arrives, the universe will be almost twice as old as it is today, and star formation will have declined significantly throughout the cosmos. Most galaxies will have exhausted much of their easily accessible hydrogen fuel, making new stellar births increasingly rare. The Andromeda merger will serve as one of the last major sources of fresh star formation in our region of space. The resulting merged galaxy, which astronomers have nicknamed Milkomeda, will contain about 1.4 trillion stars and stretch across roughly 200,000 light-years. This makes it comparable in size to the largest elliptical galaxies observed in the distant universe, cosmic giants that formed through multiple mergers in the early epochs of cosmic history. More importantly, the merger will mix together the remaining gas supplies of both galaxies, creating new reservoirs of star-forming material that would otherwise remain separated and diluted. Think of it like combining two partially empty fuel tanks to create one fuller tank that can keep an engine running longer than either tank could manage alone. The increased gravitational pull of the merged galaxy will also help it retain gas that might otherwise be lost to the expanding universe. Smaller galaxies lose their gas over time as stellar winds and supernova explosions blow material out into intergalactic space, but larger galaxies can hold onto their gas more effectively, extending their ability to form new stars. But even this galactic merger cannot change the fundamental trajectory of cosmic evolution. When the last star burns out and the final planet freezes into a ball of ice, black holes will remain as the only active objects in a universe growing colder and emptier with each passing eon. These cosmic monsters, born from the gravitational collapse of massive stars, possess the ability to survive conditions that destroy everything else, making them the universe's ultimate survivors in a cosmos destined for heat death. A black hole forms when a star, at least 25 times more massive than our Sun, runs out of nuclear fuel and collapses under its own gravity in less than 1 second. The collapse is so violent and complete that it creates a region of space where gravity becomes strong enough to trap light itself. Think of it as a cosmic pit so deep that nothing, not even the fastest thing in the universe, can climb back out once it falls past the point of no return called the event horizon. The mathematics describing black holes reveal why they survive everything else in the universe. Unlike stars, which depend on nuclear fusion to fight against gravitational collapse, black holes have already completed their collapse and reached a stable equilibrium. They do not burn fuel, generate heat, or depend on any external energy source to maintain their existence. They simply warp space and time around themselves so severely that they become permanent features of the cosmic landscape. Black holes grow stronger by consuming matter that falls into them, converting mass directly into gravitational energy according to Einstein's equation E equals mc squared. When matter crosses the event horizon, it adds to the black hole's mass and increases its gravitational pull, making it even better at capturing more material. This creates a positive feedback loop that allows black holes to grow larger and more powerful over cosmic timescales. The largest black holes, called supermassive black holes, lurk at the centers of most galaxies and contain millions or billions of times more mass than our Sun compressed into regions smaller than our solar system. The supermassive black hole at the center of our galaxy, called Sagittarius A, contains about 4 million solar masses within a diameter of only 17 million miles. If you could somehow replace our Sun with this black hole, its event horizon would fit comfortably within the orbit of Mercury. As the universe expands and cools, black holes will gradually consume everything within their gravitational reach. Dead stars, planets, asteroids, and gas clouds will slowly spiral into these cosmic vacuum cleaners over periods lasting quadrillions of years. Even objects that start very far from a black hole will eventually fall in, because the expansion of space cannot overcome gravity within the local gravitational influence of massive objects. The feeding process happens slowly but inexorably. Matter spiraling into a black hole first forms an accretion disk, where friction heats the material to millions of degrees and causes it to glow brightly before disappearing forever beyond the event horizon. During the universe's black hole era, these accretion disks will provide the only sources of light and heat in an otherwise cold and empty cosmos. Black holes also merge with each other when their host galaxies collide, creating even larger and more powerful gravitational monsters. The merger process releases enormous amounts of energy in the form of gravitational waves, ripples in space-time itself that travel at the speed of light. These cosmic collisions will continue for trillions of years as the universe's remaining matter gradually concentrates into fewer and fewer black holes of ever-increasing size. Eventually, the universe will contain only a handful of supermassive black holes separated by vast gulfs of empty space, expanding faster than light. These final survivors will drift apart as space continues expanding, becoming isolated islands of extreme gravity in an ocean of nothingness. Each black hole will sit alone in its own cosmic horizon, unable to interact with or even detect the existence of the others. But even these ultimate survivors face their own inevitable doom, because quantum mechanics has discovered a fatal flaw in their seemingly perfect defenses. For an almost incomprehensibly long period, lasting from about 100 trillion years to 10 to the 100th power years after the Big Bang, black holes will become the dominant objects in the universe, ruling over a cosmic landscape so alien that no human imagination has ever conceived anything like it. During this black hole era, these gravitational monsters will slowly consume the scattered remnants of dead galaxies while growing larger and more isolated in an ever-expanding ocean of empty space. The transition into the black hole era begins when the last red dwarf stars finally exhaust their nuclear fuel and fade into cold, dark objects called brown dwarfs. Red dwarfs burn so slowly that they can maintain nuclear fusion for up to 10 trillion years, making them the longest-lived stars in the universe. But even these cosmic misers must eventually run out of hydrogen fuel, leaving behind stellar corpses no longer capable of generating heat and light. Once stellar death becomes complete, black holes will be the only remaining objects capable of releasing energy into the universe. They accomplish this through accretion, the process of consuming matter that falls within their gravitational influence. Dead planets, asteroids, brown dwarf stars, and scattered gas clouds will slowly spiral into these cosmic drain pipes over periods lasting quadrillions of years. The accretion process creates spectacular displays of energy release as matter accelerates to nearly the speed of light before disappearing forever beyond the event horizon. Friction within the swirling accretion disk heats infalling material to temperatures exceeding billions of degrees, causing it to emit X-rays and gamma rays that outshine entire galaxies. Think of it as the universe's last fireworks show, powered by the gravitational energy of matter falling into inescapable cosmic pits. But these feeding frenzies happen infrequently and unpredictably. Most of the time, black holes sit quietly in empty space, surrounded by event horizons that stretch for millions or billions of miles, but contain nothing but vacuum and curved spacetime. A typical supermassive black hole might consume a Jupiter-sized object once every trillion years, creating a brief burst of energy followed by cosmic ages of darkness and silence. The isolation of black holes becomes more severe as space continues expanding under the influence of dark energy. Black holes that formed in the same galaxy cluster will eventually drift so far apart that light cannot travel between them, even if it had billions of years to make the journey. Each black hole becomes trapped within its own cosmic horizon, a sphere of space beyond which no information or influence can reach. During this era, the universe's temperature will drop to incredibly low levels, approaching absolute zero within a tiny fraction of a degree. The cosmic microwave background radiation will redshift into radio waves, then infrared, and finally disappear entirely as its wavelength stretches beyond the size of the observable universe itself. Space will become colder than the most sophisticated refrigeration systems humans have ever built. Black holes during this period will range in size from stellar mass objects containing only a few times the mass of our Sun to supermassive giants containing hundreds of billions of solar masses. The largest black holes will have event horizons stretching across distances comparable to the current size of our solar system, while the smallest will measure only a few miles in diameter despite containing more mass than our Sun. Occasionally, two black holes will still merge during this era when random gravitational perturbations cause their orbits to decay over extremely long time periods. These mergers will release tremendous amounts of energy as gravitational waves, creating ripples in space-time that carry away mass energy equivalent to several solar masses, converted entirely into pure motion of the cosmic fabric itself. The merger process creates a brief but intense source of gravitational radiation that would dwarf any energy release witnessed during the earlier stellar era of cosmic history. For a few minutes during the final plunge and collision, a pair of merging supermassive black holes will outshine all the energy ever produced by nuclear fusion in every star that ever existed. But even these cosmic titans cannot escape the subtle quantum processes that will eventually destroy them. In 1974, physicist Stephen Hawking made a discovery so shocking that he initially refused to believe his own calculations. Black holes are not actually black, and they slowly evaporate by emitting radiation until they disappear completely, leaving behind only empty space and a few stray particles moving at nearly the speed of light. This process, now called Hawking radiation, represents the ultimate fate of every black hole in the universe, no matter how massive or seemingly permanent they appear today. The physics behind black hole evaporation involves quantum mechanics at its most bizarre and counterintuitive. According to quantum theory, empty space is not actually empty, but filled with virtual particle pairs that pop into existence and annihilate each other in tiny fractions of a second. Near a black hole's event horizon, the intense gravitational field can separate these virtual particles before they annihilate, causing one particle to fall into the black hole while the other escapes as real radiation. Think of it like a cosmic magic trick where the black hole pays for the escaped particle's existence by giving up a tiny amount of its own mass energy. Each escaping particle carries away energy that must come from somewhere, and that somewhere is the black hole's own gravitational binding energy. Over time, this steady leak of energy causes the black hole to shrink, making its event horizon smaller and its gravitational field weaker. The temperature of Hawking radiation depends inversely on the black hole's mass, creating a paradox that seals every black hole's eventual doom. Smaller black holes radiate at higher temperatures than larger ones, which means they evaporate faster as they get smaller. A black hole with the mass of our Sun would have a temperature of only 60 billionths of a degree above absolute zero, making its evaporation rate so slow that it would take longer than 10 to the 67th power years to disappear completely. But supermassive black holes evaporate even more slowly, because their larger mass gives them lower radiation temperatures. A black hole, containing 1 billion solar masses, would take approximately 10 to the 100th power years to evaporate, a time span so vast that it makes the current age of the universe seem like a brief moment. These cosmic giants will outlive every other object in the universe by factors that human language cannot adequately express. The evaporation process accelerates as black holes shrink, creating a runaway effect that leads to explosive endings. When a black hole reaches the mass of a large mountain, about 10 to the 15th power grams, its Hawking radiation becomes hot enough to glow like a star. As it continues shrinking, the temperature rises exponentially until the final moments when the black hole explodes with the energy of millions of hydrogen bombs detonating simultaneously. This final explosion releases all the black hole's remaining mass as pure energy in less than a second, creating a brief but incredibly intense flash of gamma rays and elementary particles. The explosion will be visible across cosmic distances, serving as a beacon announcing the death of one of the universe's most enduring objects. But by the time these explosions begin, the universe will be so old and empty that no observers will likely exist to witness them. The Hawking radiation process reveals a fundamental principle about the universe. Nothing lasts forever, not even objects that seem immune to destruction. Black holes represent the most extreme gravitational systems possible in our universe, yet they still succumb to the subtle quantum effects that govern reality at its smallest scales. The battle between gravity and quantum mechanics always ends with quantum mechanics victorious. During the black hole evaporation era, the universe will be dominated by the faint glow of Hawking radiation emanating from countless black holes of various sizes. This radiation will provide the only source of energy in a cosmos that has otherwise reached thermal equilibrium at temperatures barely above absolute zero. The night sky, if anyone existed to observe it, would be filled with the ghostly light of slowly dying black holes scattered across infinite space. The largest supermassive black holes will be the last objects to evaporate, persisting until approximately 10 to the 100th power years after the Big Bang. When the final black hole finally explodes in its last burst of Hawking radiation, it will mark the end of the gravitational era of cosmic history and the beginning of a new phase dominated entirely by elementary particles and electromagnetic radiation. But before the last black holes evaporate, space itself will become more empty than most people can imagine. The universe's largest black holes face death sentences that stretch across time periods longer than the human mind can comprehend, condemned to slowly evaporate through a process so gradual it makes continental drift look like a race car crash. A supermassive black hole containing 10 billion times the mass of our Sun will require approximately 10 to the 104th power years to completely evaporate through Hawking radiation, a time span that dwarfs the current age of the universe by a factor of 10 followed by 91 zeros. To understand how slowly this process unfolds, consider that such a black hole currently loses mass at a rate of only about 10 to the negative 83rd power grams per second. This means it would take longer than the age of the universe for the black hole to lose the equivalent mass of a single proton. The radiation temperature of these cosmic giants measures only 10 to the negative 14th power degrees above absolute zero, making them colder than the cosmic microwave background radiation that currently fills empty space. This creates a bizarre situation where the largest black holes actually grow larger during the current era of cosmic history because they absorb more energy from the cosmic microwave background than they emit through Hawking radiation. They will only begin shrinking when the universe expands and cools enough that the background radiation temperature drops below their own Hawking temperature, which will not happen for approximately 10 to the 15th power years. The mathematics of black hole evaporation follow what physicists call the inverse relationship, where smaller black holes radiate away their remaining mass much faster than larger ones. When a supermassive black hole finally shrinks to only 1 million solar masses, its evaporation rate increases dramatically, and the time required to lose each additional unit of mass decreases exponentially. Think of it like a melting ice cube that loses mass slowly at first, but then disappears rapidly once it reaches a critical size. During the final stages of evaporation, when the black hole's mass drops below that of a large asteroid, the process becomes almost violent compared to the gentle radiation that characterized earlier phases. The black hole's event horizon shrinks rapidly, and its surface temperature rises to millions of degrees, causing it to glow with intense gamma radiation that can be detected across intergalactic distances. The acceleration continues until the black hole reaches what physicists call the Planck mass, approximately 22 micrograms, at which point quantum gravitational effects become so strong that our current understanding of physics breaks down completely. Some theories suggest the final evaporation happens in an explosive burst lasting less than 10 to the negative 23rd power seconds, releasing energy equivalent to approximately 1 million tons of TNT in a flash of pure radiation. This final explosion converts the black hole's remaining mass entirely into photons, neutrinos, and other elementary particles that scatter into space at the speed of light. The explosion leaves behind no remnant, no scar in space-time, and no trace that a black hole ever existed at that location. The curved space-time around the black hole simply relaxes back to flatness, like a stretched rubber sheet returning to its original shape when a heavy weight is removed. The Hawking radiation process reveals one of the most profound aspects of black hole physics. These objects have finite lifespans despite their ability to trap light and withstand any classical force that could destroy them. Even though they represent the most extreme gravitational systems possible in our universe, they still succumb to quantum mechanical effects that operate on scales billions of times smaller than atomic nuclei. Throughout their evaporation, black holes follow the laws of thermodynamics, just like any other physical system. They have temperature, entropy, and energy, and they exchange heat with their surroundings according to the same principles that govern steam engines and refrigerators. The fact that black holes obey thermodynamics suggests deep connections between gravity, quantum mechanics, an information theory that physicists are still working to understand fully. The evaporation process also raises profound questions about the fate of information that falls into black holes. According to quantum mechanics, information cannot be destroyed, but Hawking radiation appears to carry away only thermal energy with no memory of what originally fell into the black hole. This creates what physicists call the information paradox, one of the most important unsolved problems in theoretical physics. As the universe's black holes slowly evaporate over cosmic timescales, they will release vast amounts of energy back into space in the form of elementary particles and radiation. This energy release represents the final recycling of matter that was locked away inside black holes for periods exceeding the current age of the universe by countless orders of magnitude. When the last supermassive black hole finally evaporates, it will mark the end of the gravitational dominance that has shaped cosmic evolution since the formation of the first stars. After the final black hole evaporates in a burst of Hawking radiation, roughly 10 to the 100th power years from now, the universe will enter a phase so empty and cold that it defies human comprehension. Space will contain only scattered elementary particles, photons, and neutrinos drifting through an expanding void at temperatures so close to absolute zero that the difference becomes meaningless on any scale we can understand. The particle density during this era will drop to approximately 1 electron per volume of space, larger than our current observable universe. Think of it as having a single grain of sand scattered somewhere within a sphere the size of Earth, except the sphere is actually much larger and the grain of sand is much smaller. The vast majority of space will contain literally nothing except the geometric properties of spacetime itself, stretched thinner and thinner by the relentless expansion driven by dark energy. These remaining particles will be the final products of black hole evaporation. Photons with wavelengths longer than galaxies, electrons and positrons moving at relativistic speeds, and neutrinos that barely interact with anything, even when the universe was dense with matter. The photons will continue redshifting as space expands, their wavelengths growing longer until they become indistinguishable from the quantum fluctuations of empty space itself. The temperature of the universe during this phase will approach absolute zero so closely that measuring the difference would require scientific notation with hundreds of zeros in the denominator. The cosmic microwave background radiation will have redshifted completely out of existence, its energy diluted across such vast volumes of space that individual photons will be separated by distances measured in light years rather than millimeters. Even the concept of temperature becomes problematic when matter is distributed so sparsely that particles might travel for billions of years without encountering anything else. Temperature measures the average kinetic energy of particles in a system, but when particles are isolated by cosmic distances, they form no meaningful system to have a collective temperature. Each particle essentially exists in its own private universe, carrying whatever energy it possessed when the last black hole gave it birth. The expansion of space during this era will accelerate exponentially under the influence of dark energy, carrying particles apart faster than the speed of light. This does not violate relativity, because the particles themselves are not moving through space faster than light. Instead, space itself expands between them at superluminal rates. Think of it like dots drawn on a balloon that move apart when the balloon inflates, even though the dots themselves are not moving across the balloon's surface. This expansion creates what cosmologists call the de Sitter phase, named after the Dutch physicist Willem de Sitter, who first described this type of exponentially expanding spacetime. In a de Sitter universe, any 2 points separate exponentially with time, causing the observable universe from any given location to shrink rather than grow. Eventually, the cosmic horizon will contract so much that an observer could see only a tiny fraction of what is actually out there. The few remaining particles will become causally disconnected from each other, meaning that no information or influence can travel between them, even given infinite time. Each particle will exist within its own shrinking sphere of causal influence, beyond which the expansion of space prevents any contact with the rest of the universe. This creates the ultimate isolation, where each surviving remnant of matter becomes a universe unto itself. During this phase, the concept of cosmic time itself begins to lose meaning because there are no processes occurring that could serve as universal clocks. The particles drift through space in straight lines, neither interacting with each other nor undergoing any changes that would mark the passage of time. An outside observer, if one could exist, would see a static universe where nothing happens and nothing changes, even though time continues to pass. The exponential expansion driven by dark energy will continue indefinitely, making space emptier and emptier without limit. The density of matter and energy will approach zero asymptotically, meaning it gets arbitrarily close to zero, but never quite reaches it mathematically. In practical terms, the universe becomes indistinguishable from complete emptiness, while still containing a few scattered particles separated by unimaginable distances. But even in this seemingly eternal emptiness, quantum mechanics suggests that the universe might still hold surprises. For decades, physicists assumed that protons, the positively charged particles in atomic nuclei, were perfectly stable and would last forever, making them the ultimate survivors in a universe destined for heat death. But cutting-edge theories in particle physics suggest that protons may actually decay into lighter particles over time periods so vast they make the current age of the universe seem like a fleeting moment, with half-lives potentially reaching 10 to the 34th power years. The discovery that protons might be mortal comes from grand unified theories, which attempt to unify the electromagnetic, weak nuclear, and strong nuclear forces into a single mathematical framework. These theories predict that protons can decay through incredibly rare quantum processes that convert matter into energy and lighter particles like positrons, neutrinos, and photons. Think of it as the ultimate expression of Einstein's famous equation E equals mc squared, where even the most stable particles eventually surrender their mass to become pure energy. Experimental physicists have spent decades searching for evidence of proton decay in massive underground detectors filled with thousands of tons of ultra-pure water, surrounded by sensitive instruments capable of detecting the faintest flashes of light. These experiments must be conducted deep underground to shield them from cosmic rays and other sources of interference that could mimic the signal of a decaying proton. So far, no experiment has definitively observed proton decay, which means that if protons do decay, their half-life must exceed 10 to the 34th power years. This number is so large that it strains human comprehension. If you started with 10 to the 80 power protons, roughly the number of protons in the observable universe, you would have to wait 10 to the 34th power years before half of them decayed into other particles. The implications of proton decay for the far future of the universe are profound and disturbing. If protons are indeed unstable, then even after all the stars burn out and all the black holes evaporate, the remaining matter in the universe will continue to disappear as protons spontaneously convert themselves into radiation and lighter particles that may themselves be unstable. This process would unfold over timescales that make the evaporation of supermassive black holes look rapid by comparison. Long after the last black hole has disappeared in a final burst of Hawking radiation, scattered protons throughout the universe will continue their slow decay, each one representing a microscopic candle flame gradually extinguishing itself in the cosmic darkness. The decay process happens randomly for individual protons, following the same statistical rules that govern radioactive decay in elements like uranium and carbon-14. You cannot predict when any specific proton will decay, but you can calculate the probability that a given proton will survive for any particular length of time. Most protons will persist far longer than the current age of the universe, but a few unlucky ones will decay much sooner. When a proton decays, it typically produces a positron and a neutral pion, which immediately decays further into two gamma-ray photons. The positron will eventually encounter one of the universe's scattered electrons and annihilate in a flash of pure energy, adding to the thin bath of radiation that fills otherwise empty space. This represents the final conversion of matter into energy, completing a process that began with hydrogen fusion in the first stars. Different grand unified theories predict different proton lifetimes, ranging from about 10 to the 34th power years to 10 to the 40th power years, or even longer. The uncertainty reflects our incomplete understanding of physics at the energy scales where grand unification occurs, energies so high that they existed only during the first tiny fraction of a second after the Big Bang. If protons decay with the shorter predicted lifetimes, they will dominate the energy budget of the far future universe, providing more total energy release than the evaporation of all black holes combined. The universe will glow faintly with the light of proton decay for time periods exceeding the black hole era by many orders of magnitude. The possibility of proton decay also raises questions about the fundamental nature of matter and energy conservation. If protons can decay, then the matter that makes up stars, planets, and living beings is not permanent but merely borrowed from the quantum vacuum for cosmically brief periods before returning to energy and massless particles. But even if protons prove mortal, one particle has already survived everything the universe could throw at it. In the unimaginably distant future, when the universe contains only scattered elementary particles separated by distances larger than today's observable cosmos, a single proton drifts through space, experiencing time in ways that would seem impossible to any human consciousness. This particle, potentially the last surviving piece of ordinary matter in existence, witnesses the universe's approach to absolute zero while existing in a state of near-perfect isolation that transforms the very nature of temporal experience. From the proton's perspective, if we could somehow imagine it having one time passes normally, according to the laws of special relativity, the particle continues its straight-line motion through space at whatever velocity it acquired when the last black hole evaporated, neither speeding up nor slowing down because no forces act upon it in the vast emptiness. Its internal quantum properties, such as spin and electric charge, remain unchanged and unchanging across cosmic eons that dwarf the current age of the universe. But the proton's relationship to the rest of the universe undergoes a profound transformation as space continues expanding exponentially under the influence of dark energy. Objects that were once within the proton's cosmic horizon gradually disappear beyond it as space stretches faster than light can travel between them. The observable universe from the proton's reference frame shrinks rather than grows, eventually containing only itself and whatever quantum vacuum fluctuations occur in its immediate vicinity. This isolation creates a unique situation where the proton becomes causally disconnected from every other particle in the universe. No information can reach it from distant regions of space, and no influence it could hypothetically exert can affect anything beyond its shrinking sphere of causal influence. The proton essentially exists in its own private universe, with an event horizon that contracts over time rather than expanding like the event horizons around black holes. The temperature of space around the proton approaches absolute zero so closely that thermal effects become negligible compared to quantum mechanical fluctuations. At these incredibly low temperatures, the distinction between matter and empty space begins to blur, as quantum uncertainty creates virtual particle pairs that pop into existence and vanish again on timescales shorter than the proton can respond to them. From the perspective of an outside observer, if one could somehow exist in this far future era, the proton appears to move through space at constant velocity while the universe expands around it. But the concept of an outside observer becomes meaningless when the expansion has carried all other reference points beyond the cosmic horizon. The proton becomes the sole occupant of its own observable universe, defining its own reference frame for space and time. The proton's quantum properties remain stable throughout this cosmic isolation because they depend only on fundamental physical constants that do not change with time or location. Its electric charge, mass, and spin angular momentum maintain their values regardless of how empty space becomes around it. These properties represent some of the most permanent features of our universe, more enduring than stars, galaxies, or even the supermassive black holes that once dominated cosmic evolution. But the proton does experience one form of change, the continuous redshifting of any electromagnetic radiation in its vicinity. The few photons scattered throughout space by the evaporation of the last black holes will have their wavelengths stretched by the expansion of space until they become undetectable even in principle. The proton will eventually exist in a universe where electromagnetic radiation has been diluted to the point of practical non-existence. The quantum vacuum around the proton will still exhibit zero-point fluctuations, the irreducible quantum jitter that exists even in completely empty space at absolute zero temperature. These fluctuations create temporary distortions in the electromagnetic and other quantum fields, producing virtual particles that exist for brief moments before disappearing back into the vacuum. The proton interacts weakly with these fluctuations, but the interactions become increasingly rare as the universe cools and expands. If proton decay proves to be real, even this final survivor will eventually succumb to the quantum processes that convert matter into energy and lighter particles. The decay would happen randomly, following statistical laws that make it impossible to predict when any individual proton will disappear. The final proton in the universe could decay tomorrow or persist for time periods exceeding 10 to the 34th power years. When that final proton finally decays, it will mark the end of ordinary matter in the universe, converting the last remnant of the atomic nuclei that once powered stars into a few particles and photons that will continue drifting through ever-expanding space. The universe will have completed its transformation from a cosmos filled with structure and complexity to one containing only the most elementary forms of energy and matter. Yet even this transition might not represent the absolute end of cosmic evolution. Hidden within the quantum mechanical foundations of reality lurks a process so terrifying that it could instantly annihilate the entire universe without warning, transforming every atom, every black hole, and every particle into pure energy in a catastrophe that would propagate at the speed of light. This process, called false vacuum decay, depends on quantum tunneling, the bizarre ability of particles to pass through energy barriers that should be impossible to cross according to classical physics. Our universe might currently exist in what physicists call a false vacuum state, like a ball balanced on top of a hill rather than resting safely in the valley below. The ball appears stable as long as nothing disturbs it, but the slightest push could send it rolling down to a lower energy state, releasing enormous amounts of energy in the process. If our universe occupies such a false vacuum, quantum tunneling could spontaneously trigger the transition to a true vacuum state with devastating consequences. Quantum tunneling allows particles to penetrate energy barriers by borrowing energy from quantum uncertainty and paying it back so quickly that the transaction remains hidden from direct observation. Think of it as nature's ultimate loan shark operation, where particles can temporarily violate energy conservation as long as they restore the balance within time periods shorter than the Heisenberg uncertainty principle allows anyone to detect the violation. In the context of vacuum decay, quantum tunneling permits the creation of a small bubble of true vacuum within our false vacuum universe. This bubble would initially be microscopic, but once formed, it would expand at the speed of light because the true vacuum has lower energy than the false vacuum. The expanding bubble would convert everything it touches into the new vacuum state, fundamentally altering the laws of physics and destroying all existing matter and energy structures. The bubble's expansion would be completely unstoppable once it began, because nothing can travel faster than the speed of light to outrun it or send warning signals ahead of its arrival. From inside our false vacuum universe, the bubble would be invisible and undetectable until the instant it arrived, at which point everything would be transformed or destroyed so quickly that no conscious observer could even perceive what was happening. The probability of false vacuum decay depends on the detailed structure of the quantum fields that fill space, particularly the Higgs field that gives mass to elementary particles. Current measurements of the Higgs boson's mass suggest that our vacuum might indeed be metastable rather than absolutely stable, meaning it could decay, but with a probability so low that the average waiting time exceeds the age of the universe by many orders of magnitude. Calculations suggest that if our vacuum is false, the typical timescale for spontaneous decay through quantum tunneling might be around 10 to the 100 power years or longer. This makes false vacuum decay a negligible threat compared to other cosmic processes like proton decay or black hole evaporation, but it introduces an element of fundamental uncertainty into the universe's ultimate fate that cannot be eliminated through better measurements or more sophisticated theories. The energy released during false vacuum decay would dwarf any other process in the known universe. When the false vacuum converts to true vacuum, the energy difference appears as radiation and particles with such enormous energies that they would instantly vaporize anything resembling ordinary matter. The temperature inside the expanding bubble would exceed anything that existed since the first moments after the Big Bang. But the most disturbing aspect of false vacuum decay is not the energy release, but the complete transformation of physical law that would accompany it. The fundamental constants that determine how particles interact, how atoms form, and how chemistry works would all change to new values appropriate for the true vacuum state. Even if some form of matter could survive the initial energy release, it would operate according to completely different rules of physics. In the new vacuum state, electrons might not bind to atomic nuclei, making atoms impossible. The strong nuclear force might be too weak to hold protons and neutrons together, causing all atomic nuclei to fly apart instantly. Even more fundamentally, the new vacuum might not permit the existence of stable matter at all, leaving only radiation and exotic particles that cannot form complex structures. The expanding bubble of true vacuum would also carry with it new space-time geometry, potentially with different numbers of dimensions or altered properties of space and time themselves. The interior of the bubble might operate according to physics so alien that concepts like causality, locality, and even existence itself could take on completely different meanings. Despite these terrifying possibilities, false vacuum decay remains highly speculative because we do not yet understand quantum field theory well enough to calculate the relevant probabilities with confidence. The metastability of our vacuum depends on physics at energy scales far beyond what we can test directly with particle accelerators, forcing us to rely on theoretical extrapolations that could be completely wrong. More importantly, even if our vacuum is false, the timescales involved are so vast that false vacuum decay poses no practical threat to anything we care about. The Sun will exhaust its nuclear fuel, the Milky Way will collide with Andromeda, and even the largest black holes will evaporate long before quantum tunneling becomes likely to end the universe. But in the impossibly distant future, when all other processes have run their course, false vacuum decay might represent the universe's final surprise. In the far future universe, when temperatures have dropped to within a tiny fraction of absolute zero and space has expanded to incredible emptiness, the very concept of stable matter begins to break down as quantum mechanical effects that are normally negligible become the dominant forces shaping reality. Even the most fundamental particles, which have remained unchanged since the first moments after the Big Bang, may find themselves subject to decay processes that transform them into pure energy or exotic forms of matter that follow completely different physical laws. The instability of matter in the far future arises from several interconnected quantum mechanical processes that operate on vastly different timescales, but all point toward the same ultimate conclusion. Nothing lasts forever, not even the protons and electrons that make up ordinary atoms. Grand unified theories predict that protons will eventually decay into lighter particles through processes involving the conversion of quarks into leptons, transforming the building blocks of atomic nuclei into bursts of energy and exotic particles. But proton decay represents only one pathway by which matter can become unstable in the cosmic future. Even if protons prove to be perfectly stable against decay, they still face destruction through other quantum mechanical processes that become increasingly important as the universe cools and expands. Virtual particle fluctuations in the quantum vacuum can occasionally produce real particle-antiparticle pairs that materialize near isolated protons, and when antimatter encounters ordinary matter, both annihilate completely into pure electromagnetic radiation. The probability of such matter-antimatter annihilation events remains incredibly small under current conditions because the universe contains very little antimatter compared to ordinary matter. But in the far future, when matter becomes so dilute that individual particles are separated by distances larger than galaxies, even these rare quantum fluctuations can become significant over the vast timescales involved. Temperature fluctuations also threaten the stability of matter in unexpected ways. Although the average temperature of the universe approaches absolute zero in the far future, quantum mechanics prevents any system from reaching exactly zero temperature because of the fundamental uncertainty principle. This means that even in the coldest possible universe, random thermal fluctuations will occasionally give particles enough energy to overcome binding forces that normally hold them together. For isolated atoms drifting through nearly empty space, these thermal fluctuations could occasionally ionize the atoms by giving their electrons enough energy to escape from their nuclear attraction. The ionization process separates the atomic components, turning neutral atoms into free protons and electrons that may never encounter each other again due to the vast emptiness of space. More dramatically, sufficiently large thermal fluctuations could provide enough energy to trigger nuclear reactions that transform atomic nuclei into different elements or break them apart entirely. While such fluctuations are extraordinarily rare at the low temperatures expected in the far future, the timescales involved are so enormous that even processes with infinitesimally small probabilities will eventually occur. The quantum vacuum itself becomes a source of instability for matter through processes that have no classical analog. Vacuum fluctuations create temporary distortions in electromagnetic and other quantum fields that can interact with nearby particles, gradually changing their quantum states or causing them to emit radiation. These interactions are normally negligible, but they accumulate over cosmic timescales until they become significant. Even more exotic processes become possible when matter exists in the extreme isolation expected in the far future universe. Quantum tunneling allows particles to spontaneously change their internal structure without external cause, potentially converting protons into neutrons or transforming electrons into neutrinos through processes that violate conservation laws over short time periods while preserving them on average. The expansion of space itself contributes to matter instability by stretching the quantum fields that mediate interactions between particles. As space expands, the virtual particles that normally provide the forces holding matter together become increasingly redshifted and diluted, weakening the bonds that keep atomic nuclei intact and electrons bound to atoms. String theory and other advanced physical theories suggest even more exotic forms of matter instability that could become relevant in the far future. If our universe has more than the three spatial dimensions we observe directly, matter might be able to tunnel into these extra dimensions and disappear from our observable reality entirely. Such processes would make particles vanish without leaving behind any detectable decay products. The mathematical description of matter instability in the far future requires sophisticated techniques from quantum field theory and statistical mechanics that push the boundaries of current theoretical physics. The calculations involve summing over all possible quantum processes that could affect isolated particles over time periods longer than the current age of the universe, by factors of trillions or more. But perhaps the most profound implication of matter instability is philosophical rather than physical. As cosmic time stretches toward infinity, and the universe continues its relentless expansion under the influence of dark energy, the temperature of space itself approaches the ultimate lower limit allowed by physics. Absolute zero, the point at which all thermal motion ceases and matter reaches its lowest possible energy state. But quantum mechanics ensures that the universe can never quite reach this perfect coldness, leaving behind a final temperature that hovers just above zero by the smallest possible amount allowed by the fundamental laws of nature. Currently, the cosmic microwave background radiation gives space an average temperature of negative 454.76 degrees Fahrenheit, or 2.7 degrees above absolute zero on the Kelvin scale. This represents the cooled remnant of the Big Bang's initial heat, stretched and diluted by nearly 14 billion years of cosmic expansion. As space continues expanding, this background radiation will redshift to longer and longer wavelengths while its temperature drops correspondingly. The mathematics of cosmological cooling follow a simple but inexorable pattern. As the universe doubles in size, its temperature drops by half. Since dark energy drives exponential expansion, the cooling also follows an exponential curve toward absolute zero. In principle, this process could continue forever. With the temperature approaching zero asymptotically but never quite reaching it, like a mathematical limit that can be approached arbitrarily closely but never achieved. But quantum mechanics imposes a fundamental lower limit on how cold the universe can become. Even at absolute zero temperature, quantum systems retain what physicists call zero-point energy, the irreducible minimum energy that exists due to the Heisenberg uncertainty principle. This zero-point energy manifests as persistent quantum fluctuations in all fields, creating a form of activity that cannot be eliminated no matter how cold space becomes. These quantum fluctuations mean that even empty space at absolute zero temperature still contains virtual particle pairs popping into existence and disappearing again on timescales shorter than the uncertainty principle allows direct observation. The energy associated with these fluctuations sets a lower bound on the universe's temperature that cannot be reduced further, no matter how much space expands or how much time passes. The final temperature of the universe will be determined by the balance between the cooling effects of cosmic expansion and the heating effects of quantum vacuum fluctuations. Current calculations suggest this equilibrium temperature will be incredibly small, perhaps 10 to the negative 30th power degrees above absolute zero, but still greater than zero by a measurable amount that reflects the fundamental graininess of quantum reality. At these ultimate low temperatures, the distinction between matter and empty space begins to blur because thermal energy becomes negligible compared to quantum mechanical effects. Particles will move so slowly that their quantum wave properties become more important than their classical particle properties, creating a universe where matter behaves more like slowly evolving quantum fields than discrete objects moving through space. The approach to absolute zero will happen gradually over time, scales that dwarf all other cosmic processes. Even after the last black holes evaporate and the last protons decay, the universe will continue cooling as space expands and dilutes the remaining energy. The cooling process will slow down as the temperature approaches its quantum mechanical limit, taking longer and longer to remove each additional increment of thermal energy. This ultimate cooling creates conditions unlike anything that has ever existed in the universe's history. During the hot, dense early moments after the Big Bang, thermal energy dominated all other forms of energy and drove rapid changes in the structure of space and time. In the final cold phase, quantum vacuum energy will dominate, creating a static universe where virtually nothing happens and time itself becomes almost meaningless. The few particles that remain at these ultimate low temperatures will exist in their quantum mechanical ground states, the lowest energy configurations allowed by the laws of physics. They will drift through space in perfectly straight lines because no thermal agitation exists to disturb their motion, and they will remain in these states indefinitely unless disturbed by rare quantum fluctuations. Paradoxically, the approach to absolute zero represents both the universe's death and its most stable possible state. All the complex structures that characterize our current universe, from stars and galaxies to planets and life, depend on temperature differences that drive energy flows and enable change. When these temperature differences disappear, no further evolution becomes possible, but the resulting state achieves a kind of eternal stability that earlier, more dynamic phases of cosmic history could never maintain. The quantum vacuum fluctuations that prevent the universe from reaching exactly absolute zero also ensure that some form of activity will persist forever, even if at levels so subtle that they would be undetectable by any conceivable measurement device. These fluctuations represent the universe's final heartbeat, a quantum mechanical pulse that will continue as long as space and time exist. But this seemingly eternal stability might still face one final challenge that could transform everything we think we know about the cosmos. Deep within the quantum structure of empty space lurks a possibility so catastrophic that it could instantly rewrite the fundamental laws of physics across the entire universe, transforming every particle, every force, and every constant of nature into something completely alien. This process, called vacuum decay, would propagate outward from its point of origin at exactly the speed of light, creating an expanding sphere of new reality that consumes everything in its path without warning or possibility of escape. The threat arises from the possibility that our universe currently exists in what physicists call a metastable vacuum state, similar to water that has been supercooled below its freezing point but hasn't yet crystallized into ice. Such water appears stable and behaves normally until a single disturbance triggers instant freezing throughout the entire volume. Our vacuum might be supercooled in a similar way, waiting for the right quantum fluctuation to trigger its collapse into a lower energy state. The quantum fields that fill all of space, including the Higgs field responsible for giving particles their mass, might currently exist at local energy minima rather than the absolute minimum possible. Think of these fields as balls sitting in shallow bowls on top of a table, appearing stable until something pushes them hard enough to roll off the table and fall to the floor below. The energy difference between the false vacuum and true vacuum states could be enormous, equivalent to the mass energy of countless stars compressed into every cubic inch of space. When vacuum decay begins, it starts with a microscopic bubble of true vacuum forming spontaneously through quantum tunneling. This bubble initially measures smaller than an atomic nucleus, but it contains space with fundamentally different properties than the false vacuum surrounding it. The boundary between true and false vacuum races outward at the speed of light, converting everything it encounters into the new vacuum state. From inside our false vacuum universe, the approaching bubble wall would be completely invisible and undetectable until the instant it arrives. No warning signals could outrun the bubble because electromagnetic radiation travels at the same speed as the vacuum decay front. One moment, everything would appear normal according to our familiar laws of physics. The next moment, those laws would no longer exist, replaced by completely different rules governing how matter and energy behave. The energy released during vacuum decay would exceed anything else in the known universe. When the false vacuum converts to true vacuum, the energy difference appears as intense radiation and exotic particles moving at nearly the speed of light. This energy release would be so violent that it would instantly vaporize every atom, every planet, every star, and every black hole, reducing them to elementary particles and pure electromagnetic radiation. But the destruction of existing matter represents only the beginning of vacuum decay's transformative power. The true vacuum state would operate according to different values of the fundamental constants that govern particle physics. The strength of electromagnetic forces, the masses of electrons and quarks, and even the number of spatial dimensions could all change to new values appropriate for the lower energy vacuum state. In this new reality, atoms might be impossible because electrons could not bind to atomic nuclei. The strong nuclear force might be too weak to hold protons and neutrons together, causing all atomic nuclei to disintegrate instantly. Even more fundamentally, the new vacuum might not permit stable matter to exist at all, supporting only radiation and exotic particles that follow completely alien physical laws. The altered space-time geometry inside the true vacuum bubble could also change the very nature of existence itself. Time might flow differently, or space might have additional dimensions that were previously hidden or compactified. The concepts of causality, locality, and conservation laws that define our current understanding of physics could be replaced by principles so foreign that they defy human comprehension. Current measurements of particle physics parameters suggest that our vacuum might indeed be metastable rather than absolutely stable. The mass of the Higgs boson, combined with the masses of other fundamental particles, places our universe tantalizingly close to the boundary between stability and metastability. Small changes in these measurements could tip the balance either way. The probability of spontaneous vacuum decay depends on quantum tunneling rates that are extraordinarily difficult to calculate precisely. Current estimates suggest that if our vacuum is false, the typical waiting time for decay might exceed 10 to the 100 power years, making it irrelevant compared to other cosmic processes like stellar evolution and black hole evaporation. Yet the possibility of vacuum decay introduces an element of fundamental uncertainty into the universe's fate that cannot be eliminated through better observations or more sophisticated theories. Even if the probability is infinitesimally small, the The consequences would be so complete and irreversible that vacuum decay represents the ultimate wildcard in cosmic evolution. But if vacuum decay never occurs, the universe faces an even stranger fate, as the only remaining entities become pure information. In the ultimate future of our universe, when all matter has decayed, all black holes have evaporated, and space has cooled to within quantum fluctuations of absolute zero, physicists believe that information might be the only thing that survives, encoded in the correlations between scattered particles and the quantum states of electromagnetic radiation propagating through otherwise empty space. This information represents everything that ever happened in cosmic history, from the formation of the first stars to the thoughts of the last conscious beings, preserved in a form that transcends the destruction of all physical structures. The concept that information is fundamental to reality emerges from quantum mechanics and thermodynamics, which together suggest that information cannot be created or destroyed, only transformed from one form to another. When a star explodes as a supernova, the information describing its internal structure and nuclear composition does not vanish, but becomes encoded in the patterns of elements scattered through space and the gravitational waves rippling outward from the explosion site. Similarly, when black holes evaporate through Hawking radiation, they must somehow preserve all the information that ever fell into them during their lifetimes. This requirement leads to what physicists call the information paradox. Hawking radiation appears to be completely random thermal emission, yet quantum mechanics demands that it must carry away precise information about everything the black hole consumed, encoded in correlations too subtle for current technology to detect. The resolution of this paradox suggests that information exists at a more fundamental level than matter or energy, serving as the basic currency from which physical reality emerges. Think of particles and forces as temporary patterns in an underlying sea of information, like waves on the ocean surface that rise and fall while the water itself remains. When the waves disappear, the ocean continues to exist, carrying within its depths the memory of every disturbance that ever occurred. In the far future universe, this informational substrate will manifest as quantum entanglement between widely separated particles and correlation patterns in the cosmic background radiation. Two electrons on opposite sides of the observable universe might share entangled quantum states that preserve information about their common origin billions of years earlier, when they were created in the same stellar nuclear reaction. The electromagnetic radiation filling space will also carry vast amounts of information in the precise frequencies, polarizations, and arrival times of individual photons. This information encodes the complete history of every object that ever emitted or scattered light, from the cosmic microwave background radiation that preserves details about the universe's first 300,000 years to the final gamma rays released by the last evaporating black holes. But accessing this information becomes increasingly difficult as the universe expands and cools. The information spreads across ever larger volumes of space, while the energy available to process it approaches zero. Future civilizations, if any could exist in such conditions, would face fundamental thermodynamic limits on their ability to extract meaningful patterns from the informational noise-filling empty space. The information itself remains perfectly preserved according to the laws of quantum mechanics, but it becomes practically inaccessible because reading it would require more energy than the universe contains. Think of it like a book written in disappearing ink that fades so slowly. The text remains technically present, but becomes too faint to read without destroying the pages in the process of illuminating them. This creates a profound paradox about the nature of existence in the far future. The universe will contain complete information about every event in cosmic history, including the thoughts and experiences of every conscious being that ever lived, but this information will be scattered across such vast distances and encoded in such subtle correlations that no physical process can retrieve it. Some theoretical physicists speculate that consciousness itself might be an informational pattern that could persist in this far future universe, existing as pure information without requiring a physical substrate. If consciousness is fundamentally about information processing rather than the specific material that performs the processing, then awareness might survive the death of all matter by existing as patterns in the quantum correlations between particles. This possibility suggests that the far future universe might not be as empty and lifeless as it appears from a purely physical perspective. The information content could support forms of existence and experience that transcend our current understanding of life and consciousness, operating according to principles that have no analog in the material world we know today. The information preserved in the far future universe will also include the complete mathematical description of physical laws themselves, encoded in the patterns of particle interactions and field correlations observed over cosmic history. This means the universe will contain within itself a perfect record of how physics works, written in the language of quantum states and correlation functions rather than human mathematics. But even information faces challenges in a universe approaching maximum entropy, where all useful energy gradients have been exhausted and no work can be performed to process or manipulate the data. The information becomes like a library in a world without electricity, containing all knowledge but lacking the energy needed to access it. Yet quantum mechanics suggests that even this informational dark age might not represent the absolute end of cosmic evolution. Somewhere in the vast expanse of space, perhaps in a galaxy billions of light years away, or maybe in the quantum foam right next to you, a bubble of altered reality, no larger than a proton, could be forming at this very moment, preparing to expand at the speed of light and consume our entire universe in a transformation so complete that it would erase every law of physics we have ever discovered. This bubble, born from the quantum tunneling of the vacuum state itself, would be invisible and undetectable until the instant it arrived, bringing with it a new form of existence that operates according to completely alien principles. The bubble begins when quantum fluctuations spontaneously create a microscopic region where the fabric of space-time itself transitions from our current vacuum state to a lower energy configuration. Think of it like a soap bubble forming in a bathtub, except this bubble contains space with fundamentally different properties than the space surrounding it. The walls of the bubble represent a boundary between two different versions of reality, each operating according to its own set of physical laws. Once formed, the bubble cannot shrink or disappear because the true vacuum inside has lower energy than the false vacuum outside. Energy always flows from higher to lower states, so the bubble wall moves outward, converting false vacuum into true vacuum as it expands. The expansion happens at exactly the speed of light because the bubble wall represents a disturbance in space-time itself, and such disturbances cannot propagate faster than light, according to Einstein's theory of relativity. From our perspective, inside the false vacuum, the approaching bubble would remain completely invisible because no information can travel faster than light to warn us of its approach. Electromagnetic radiation, gravitational waves, and any other signals that might reveal the bubble's existence would arrive at exactly the same moment as the bubble wall itself, providing zero advance warning of the impending transformation. The energy released when false vacuum converts to true vacuum would exceed the total energy output of all stars that have ever existed in the observable universe. This energy appears instantaneously as the bubble wall passes through matter, converting the vacuum energy difference into intense radiation and exotic particles moving at relativistic speeds. Every atom would be torn apart and vaporized in a burst of energy so violent it would make supernova explosions look like firecracker pops. But the complete annihilation of existing matter represents only the beginning of the bubble's transformative power. Inside the true vacuum, the fundamental constants of nature would take on different values, potentially making atoms impossible, changing the strength of nuclear forces, or altering the properties of space and time themselves. The speed of light might be different, gravity might be stronger or weaker, and even the number of spatial dimensions could change. In this new reality, the particles that survive the initial energy release would behave according to completely unfamiliar rules. Electrons might not be able to orbit atomic nuclei, making chemistry impossible. The strong nuclear force might be too weak to bind protons and neutrons together, causing all atomic nuclei to fly apart instantly. Even more radically, stable matter might not be able to exist at all in the true vacuum state. The bubble's expansion would be completely unstoppable once it began, because nothing can travel faster than light to interfere with its progress. Even if we could somehow detect the bubble's approach, which physics tells us is impossible, we would have no way to escape or defend against it. The transformation would overtake us at the same speed that information about its existence could reach us. The mathematics describing false vacuum decay suggests that such bubbles could form spontaneously at any time through quantum tunneling, but the probability remains so low that the expected waiting time exceeds the current age of the universe by many orders of magnitude. Current estimates place the typical time between spontaneous bubble formations at roughly 10 to the 100 power years, making false vacuum decay irrelevant compared to other cosmic processes like stellar evolution and black hole evaporation. But the probability calculations depend on our understanding of particle physics at energy scales far beyond what we can test directly with experiments. Small changes in the masses of fundamental particles or the strength of their interactions could dramatically alter the tunneling rates, either making vacuum decay more likely or proving that our vacuum is actually stable against all possible fluctuations. The expanding bubble would also carry with it new space-time geometry that could change the fundamental structure of reality. Time might flow differently inside the bubble, or additional spatial dimensions might become visible that were previously hidden or compactified. The concepts of causality, conservation laws, and even existence itself might take on completely different meanings in the true vacuum state. If multiple bubbles formed in different regions of space, they would expand independently until their boundaries collided, creating interfaces between different true vacuum states that could generate even more exotic physics. The collision zones might support particles and interactions that exist nowhere else in either vacuum state, creating temporary bridges between incompatible realities. Despite the terrifying implications of false vacuum decay, it remains highly speculative because we lack the theoretical tools to calculate the relevant quantum tunneling rates with confidence. In the unimaginably distant future, when the universe has expanded so much that galaxies have drifted beyond each other's cosmic horizons, and the last black holes have evaporated into Hawking radiation, even photons, the particles of light that have traveled freely through space since the first moments after the Big Bang will find themselves trapped in a cosmos with no destinations left to reach and no matter left to interact with, condemned to drift through expanding emptiness for time periods that make eternity seem brief. These photons represent the final electromagnetic radiation in the universe, released by the evaporation of the last black holes or the decay of the last protons, carrying energy levels so low that their wavelengths stretch across distances larger than entire galaxies. They propagate through space at the speed of light, as they always have. But space itself expands faster than they can travel to reach any remaining matter that might absorb them and convert their energy into other forms. The expansion of space continuously redshifts these photons, stretching their wavelengths longer and longer while decreasing their energy correspondingly. A gamma-ray photon released by the final black hole evaporation will gradually redshift through X-rays, ultraviolet, visible light, infrared, and radio waves, eventually reaching wavelengths measured in miles, then thousands of miles, then distances comparable to the size of planets, solar systems, and finally entire galaxies. As the wavelengths grow longer, the photon's energy decreases proportionally, approaching zero asymptotically but never quite reaching it because massless particles always travel at the speed of light, and therefore always possess some finite energy. Think of it like a ball rolling uphill on a slope that gets gentler and gentler but never becomes completely flat, so the ball slows down but never stops moving entirely. The redshifting process continues indefinitely as long as space keeps expanding, which current observations suggest it will do forever under the influence of dark energy. Eventually, individual photons will have wavelengths larger than the observable universe itself, making them impossible to detect even in principle because no measurement device could be large enough to span a complete wavelength. But even these ultra-long wavelength photons continue to exist and propagate through space, carrying infinitesimal amounts of energy across cosmic distances that grow exponentially with time. They represent the universe's final memory of the matter and energy that once filled space with structure and complexity, preserved in electromagnetic form long after their sources have vanished completely. The photons also become increasingly isolated from each other as space expands. Initially, the final burst of Hawking radiation from an evaporating black hole might produce billions of photons in a brief flash lasting microseconds. But as these photons spread out through expanding space, the average distance between them grows until each photon occupies its own vast region of space with no other photons anywhere nearby. This isolation means that photons lose the ability to interfere with each other, even in principle. Quantum interference effects, which depend on photons being close enough together for their wavefronts to overlap, become impossible when the photons are separated by distances that light cannot cross in billions of years. Each photon effectively exists in its own private universe, unable to interact with anything else. The lack of matter in the far future universe also eliminates all possible mechanisms for photon absorption or scattering. Photons interact with matter through electromagnetic forces, but when no charged particles remain to interact with, the photons simply continue propagating forever without any possibility of transferring their energy to other systems. They become truly eternal travelers, with nowhere to go and nothing to do when they arrive. Some photons might occasionally interact with virtual particle pairs that spontaneously appear in the quantum vacuum, but these interactions become increasingly rare as the universe cools and the photon energies drop due to redshifting. The cross-sections for such interactions decrease rapidly with photon energy, making them negligible for the ultra-low energy photons that exist in the far future. The photons also lose their directional meaning as space expands faster than light. Photons that started out traveling toward distant galaxies will find that their destinations have moved beyond the cosmic horizon, carried away by the expansion of space faster than the photons can pursue them. The photons continue traveling in straight lines through space, but their targets no longer exist within the causal universe they can ever reach. In this strange, far-future cosmos, photons become like messages in bottles thrown into an ocean that grows larger faster than the bottles can travel, ensuring that they will never reach any shore or be found by any receiver. They carry information about the universe's past encoded in their wavelengths and polarizations, but this information becomes inaccessible because no physical process can decode it. The mathematical description of photon evolution in the expanding universe follows the geodesics of curved spacetime, showing that these particles will continue their journeys through space for infinite time, gradually losing energy to redshift, but never disappearing completely. They represent the universe's most persistent remnants, outlasting stars, black holes, and even the protons that once formed the building blocks of matter. Yet even as photons face this eternal isolation, other quantum processes continue to unfold in the vacuum around them. As the universe expands toward its ultimate cold and empty future, when all stars have burned out, all black holes have evaporated, and even protons have decayed into lighter particles, quantum fluctuations in the vacuum become the only processes still capable of creating change and marking the passage of time. These spontaneous appearances and disappearances of virtual particle pairs represent the universe's final heartbeat, the last form of activity that will persist, even when everything else has achieved perfect thermal equilibrium at temperatures approaching absolute zero. Quantum fluctuations arise from the fundamental uncertainty principle, which prevents any quantum field from remaining perfectly motionless even at absolute zero temperature. The vacuum itself constantly bubbles with virtual particles that pop into existence in matter-antimatter pairs, exist for brief moments determined by their mass and energy, then annihilate each other and disappear back into nothingness. Think of it as the universe's quantum metabolism, an irreducible activity that continues even when no macro-scale events occur anywhere in the cosmos. In the current universe, these vacuum fluctuations are usually overwhelmed by much larger energy processes like stellar nuclear fusion, gravitational interactions, and thermal motion of particles. But in the far future, when the universe has cooled to within quantum mechanical limits of absolute zero and expanded until matter density approaches zero, vacuum fluctuations become the dominant form of energy and the only source of change in an otherwise static cosmos. The energy scale of these fluctuations is incredibly small, typically involving particles with masses equivalent to individual photons or electrons, appearing for time periods shorter than the time light takes to cross an atomic nucleus. But when no other processes compete with them, these tiny quantum events become the most significant things happening anywhere in the universe, the only phenomena capable of disturbing the perfect stillness of thermal equilibrium. The fluctuations occur randomly throughout space, according to quantum mechanical probability distributions that cannot be predicted for individual events, but follow statistical patterns over large volumes and long time periods. Occasionally, a virtual particle pair will appear near one of the few remaining real particles in the universe, creating a brief interaction before the virtual particles annihilate and disappear again. These interactions can cause real particles to change their quantum states, emit photons, or alter their trajectories through space in subtle ways that would be completely undetectable by any conceivable measurement device. The changes are so small they barely qualify as events in the traditional sense, yet they represent the only form of cosmic evolution still occurring in a universe that has otherwise reached maximum entropy and thermal death. The timescales between significant quantum fluctuation events become astronomically long as the universe expands and cools. In dense, hot environments like stellar cores, vacuum fluctuations occur trillions of times per second in every cubic inch of space. But in the cold, empty far future, a typical volume the size of our current observable universe might experience only one detectable quantum fluctuation every 10 to the 50th power years. But these rare events accumulate over the vast timescales available in the far future universe. Given enough time, quantum fluctuations can accomplish seemingly impossible feats, like spontaneously creating complex structures from pure vacuum, or causing particles to tunnel across barriers that classical physics says they cannot cross. The probability of any specific fluctuation remains tiny, but infinity is a very long time for improbable events to occur. One of the most remarkable possibilities involves quantum fluctuations spontaneously creating entire regions of space with different vacuum states, effectively generating new universes with their own physical laws embedded within our dying cosmos. These bubble universes would expand and evolve according to their own rules, potentially recreating conditions similar to our early universe and beginning new cycles of cosmic evolution. The mathematics describing vacuum fluctuations in empty space involve sophisticated quantum field theory calculations that push the boundaries of current theoretical physics. The results suggest that even apparently empty space contains infinite amounts of zero-point energy distributed across all possible quantum fields, creating a seething foam of virtual activity at scales smaller than atomic nuclei. This quantum foam becomes the dominant texture of space-time in the far future universe, determining how the few remaining particles move and interact with each other. The foam is invisible and undetectable by ordinary means, but it provides the stage on which the universe's final drama plays out, one virtual particle at a time. Quantum fluctuations also provide the mechanism by which the universe could potentially escape from thermal death through extremely rare but not impossible events that create pockets of low entropy within the overall high entropy environment. These rare fluctuations could spontaneously organize energy and matter into complex structures, effectively reversing the thermodynamic arrow of time locally while preserving it globally. The concept that quantum fluctuations become the universe's primary activity in the far future represents one of the strangest predictions of modern physics, suggesting that reality at its most fundamental level is characterized by constant change and uncertainty, rather than the static perfection that classical physics would expect at thermal equilibrium. Yet even these quantum fluctuations must eventually confront the evaporation of the final gravitational structures. In approximately 10 to the 100th power years from now, the last supermassive black hole in the universe will finally succumb to Hawking radiation and evaporate completely, marking the end of the gravitational era that has dominated cosmic evolution since the first stars collapsed to form these cosmic monsters. This final evaporation will release the equivalent energy of trillions of stars, converted entirely into electromagnetic radiation and elementary particles, creating the universe's last great fireworks display before settling into eternal darkness and cold. The final black hole will likely be one of the supermassive giants that currently lurk at the centers of galaxies, containing billions of times the mass of our Sun compressed into a region smaller than our solar system. By the time it begins its final evaporation, this black hole will be the only remaining object in its cosmic neighborhood capable of generating significant amounts of energy. Surrounded by empty space that has expanded and cooled for periods exceeding the current age of the universe by factors too large for human comprehension. Throughout most of its existence, this black hole will evaporate so slowly that its mass loss appears negligible, even over cosmic timescales. A black hole containing 10 billion solar masses loses only about 10 to the negative 83rd power grams per second through Hawking radiation, a rate so slow that it would take longer than 10 to the 100th power years to shrink by even 1%. The black hole remains essentially constant in size while the universe expands around it, making it appear increasingly dominant relative to its ever-emptying surroundings. But the evaporation process accelerates dramatically as the black hole shrinks because smaller black holes have higher Hawking temperatures and radiate energy faster than larger ones. When the final black hole finally drops below about 1 million solar masses, its evaporation rate begins increasing exponentially, and the time required to lose each additional unit of mass decreases rapidly, according to the inverse cube relationship between mass and evaporation time. During the final million years of the black hole's existence, it will release more energy than it emitted during the previous 10 to the 100th power years combined. The black hole's event horizon will shrink visibly, contracting from a diameter of millions of miles to thousands of miles to hundreds of miles as the evaporation accelerates toward its explosive conclusion. The Hawking radiation during this final phase will shift from incredibly long wavelength radio waves to shorter wavelengths, eventually reaching visible light when the black hole shrinks to about the mass of a large asteroid. An observer positioned safely outside the black hole's influence would see it begin to glow like a star, growing brighter and hotter as it approaches its final moments of existence. When the black hole reaches approximately the Planck mass, about 22 micrograms, quantum gravitational effects become so strong that our current understanding of physics breaks down completely. The evaporation might end in an explosive burst lasting less than 10 to the negative 23rd power seconds, releasing energy equivalent to approximately 1 million tons of TNT in a flash of pure gamma radiation and elementary particles. This final explosion will convert the black hole's remaining mass entirely into photons, neutrinos, electrons, positrons, and other light particles that scatter into space at nearly the speed of light. The explosion leaves behind no remnant, no scar in space-time, and no memory that a black hole ever existed at that location, except for the particles and energy it released during its death. The curved space-time around the evaporating black hole will relax back to flatness like a stretched rubber sheet, returning to its original shape when a heavy weight is removed. The gravitational waves generated by this relaxation will ripple outward at the speed of light, carrying away the last traces of the black hole's influence on the geometry of space and time. With the evaporation of the final black hole, the universe will have completed its transition from a cosmos dominated by gravitational structures to one containing only elementary particles and electromagnetic radiation distributed uniformly through ever-expanding space. No more black holes will ever form because insufficient matter remains anywhere in the universe to collapse under its own gravity and create new ones. The energy released by the final black hole evaporation will briefly heat the surrounding space to temperatures not seen since the early moments after the Big Bang, but this heat will quickly disperse and redshift away as space continues expanding. Within a few million years after the explosion, the universe will return to its inexorable cooling toward absolute zero, leaving behind only the scattered particles and photons from the black hole's death. The particles created by the final evaporation will themselves be subject to further decay processes if protons prove unstable, or they will simply drift through expanding space forever if protons are truly immortal. Either way, the evaporation of the last black hole marks the end of an era that began with the first stellar collapses only a few 100 million years after the Big Bang. But even after this final gravitational death, time itself continues its strange relationship with the remaining universe. In the far future universe, when the last black hole has evaporated and only scattered elementary particles drift through space, expanding faster than light, the concept of time begins to lose its meaning in ways that challenge our most fundamental assumptions about the nature of reality. Without change, without events, and without any processes that could serve as universal clocks, time becomes an abstract mathematical parameter that describes nothing observable or meaningful to any hypothetical observer who might still exist in such a cosmos. Time, as we understand it, depends on change to give it meaning and measurability. We define seconds by the oscillations of atoms, years by planetary orbits, and cosmic epochs by the evolution of stars and galaxies. But when the universe reaches thermal equilibrium at temperatures approaching absolute zero, these changes cease to occur. Particles drift through space in straight lines at constant velocities, neither speeding up nor slowing down, neither colliding with each other nor undergoing any transformations that would mark the passage of temporal duration. The few remaining particles become so isolated by the expansion of space that they exist in completely separate causal regions, unable to influence each other or share information about their states. Each particle defines its own reference frame for space and time, but these reference frames have no connection to each other and no common basis for establishing simultaneity or temporal ordering of events across cosmic distances. Einstein's theory of relativity already showed us that time is relative rather than absolute, depending on the motion and gravitational environment of the observer. In the far future universe, this relativity becomes extreme because no universal reference frame exists to coordinate the measurement of time intervals. Each isolated particle essentially exists in its own private universe, where time passes normally from its perspective. But this local time has no meaning or relevance to anything happening elsewhere in the cosmos. The expansion of space itself, driven by dark energy, creates additional complications for the concept of cosmic time. Different regions of space expand at different rates depending on their local matter and energy density, causing time to flow differently in various parts of the universe. What might be simultaneous from one perspective could be separated by billions of years from another perspective, making the concept of universal time completely meaningless. Quantum mechanics adds another layer of temporal strangeness to the far future universe. The quantum states of isolated particles evolve according to the Schrödinger equation, but this evolution becomes purely formal when no measurements or interactions occur to collapse the wave functions into definite states. The particles exist in quantum superpositions that persist indefinitely, neither changing nor remaining the same in any classical sense. The mathematical description of time in the far future universe reduces to what physicists call a parameterization of the particle trajectories through spacetime. Time becomes simply a label that mathematicians use to organize their equations, rather than a physical quantity that corresponds to anything observable or measurable in the real world. This loss of temporal meaning creates profound philosophical puzzles about the nature of existence itself. If nothing changes and no events occur, in what sense can we say that time passes or that the universe continues to exist? The particles and photons scattered through space maintain their quantum properties and continue their motion, but without any context or reference frame to give this motion significance. Some physicists speculate that consciousness itself might be necessary to give time its meaning, because consciousness creates the subjective experience of temporal flow and the sense that events occur in sequence rather than simply existing as abstract mathematical relationships. In a universe without conscious observers, time might become nothing more than a coordinate axis in the equations of theoretical physics. But even without conscious observers, quantum mechanical processes continue to occur through virtual particle fluctuations in the vacuum, and these fluctuations could potentially serve as a fundamental clock that gives meaning to temporal intervals. The fluctuations happen randomly, but they follow statistical patterns that could, in principle, be used to measure the passage of time even when no other changes occur. The concept of entropy also provides a potential arrow of time that persists even in the thermal equilibrium of the far future. Although the universe reaches maximum entropy overall, local fluctuations can temporarily decrease entropy in small regions of space, creating brief departures from equilibrium that mark temporal direction, even when no other changes are visible. The mathematics of quantum field theory in curved spacetime suggests that time retains its mathematical structure even when it loses its physical meaning, continuing to serve as a parameter that describes the evolution of quantum states according to fundamental equations of motion. Time becomes like the mathematical concept of infinity, perfectly well defined in abstract terms, but impossible to observe or experience directly. This temporal paradox represents one of the deepest mysteries about the ultimate fate of our universe, raising questions about whether existence itself has meaning in the absence of change, and whether the concepts we use to understand reality retain their validity when applied to cosmic scales that transcend all human experience. Yet even as time loses its meaning, the universe retains the capacity for one final surprise. Deep in the far future, when the universe has cooled to temperatures barely distinguishable from absolute zero, and matter has spread so thin that individual atoms are separated by distances larger than galaxies, quantum mechanics still permits one final chemical reaction to occur: the formation of a hydrogen molecule from two isolated protons and two electrons that randomly encounter each other in the vast emptiness of space. This reaction, requiring a probability so low it defies imagination, represents the universe's last attempt to create molecular complexity before succumbing completely to thermal death. The reaction begins when two hydrogen atoms, drifting through space for trillions upon trillions of years, happen to pass within a few atomic diameters of each other. At the incredibly low temperatures of the far future universe, the atoms move so slowly that quantum mechanical tunneling effects become significant, allowing their electron clouds to overlap and form chemical bonds even when they lack the thermal energy that normally drives molecular formation. Under current conditions on Earth, hydrogen molecules form easily when hydrogen atoms collide with sufficient energy to overcome the small activation barrier required for bond formation. But in the far future universe, thermal energies will be so low that classical chemical reactions become impossible. Only quantum tunneling allows the electrons to penetrate the energy barriers that separate individual atoms from molecular bonds. The probability of this quantum tunneling event is astronomically small, requiring the precise alignment of quantum phases and energy levels across time periods that exceed the current age of the universe by factors measured in googol's. Think of it like winning the lottery every second for a trillion years, except the odds are infinitely worse and the time periods are infinitely longer. But infinity is a very long time for improbable events to occur. Given enough time, even processes with vanishingly small probabilities will eventually happen through the random fluctuations of quantum mechanics. The far future universe has unlimited time available for these rare quantum events to manifest themselves through sheer statistical inevitability. When the tunneling finally occurs, the two hydrogen atoms will suddenly find themselves bound together by shared electrons in a configuration that represents the most stable molecular structure possible under the extreme conditions of the far future cosmos. The newly formed hydrogen molecule will be incredibly cold, possessing only the minimal zero-point energy required by quantum mechanics and moving through space at whatever velocity its constituent atoms had before they bonded together. The formation of this molecule will release a tiny amount of binding energy, perhaps equivalent to a single infrared photon, into the surrounding vacuum. This photon will represent one of the last energy-releasing processes in the universe, a final conversion of potential energy into electromagnetic radiation that will propagate through space until it redshifts into virtual non-existence. The hydrogen molecule itself will be remarkably stable once formed, because breaking the chemical bond would require energy that simply does not exist anywhere in the cold, empty, far future universe. The molecule will persist indefinitely, unless it encounters one of the extremely rare quantum fluctuations, capable of providing enough energy to dissociate it back into individual atoms. More exotic chemical reactions might also become possible on these vast timescales, such as the formation of hydrogen ions through interactions with virtual particles in the quantum vacuum, or the creation of temporary molecular complexes that exist for brief moments before thermal fluctuations tear them apart again. Each reaction would represent a microscopic victory of organization over entropy, temporary islands of molecular complexity in an ocean of cosmic disorder. The mathematics describing these ultra-rare chemical reactions requires sophisticated quantum mechanical calculations that account for tunneling probabilities, zero-point motions, and the effects of the expanding space-time metric on molecular binding energies. The results suggest that chemical complexity could persist at unimaginably low levels, even in the universe's final equilibrium state. But the formation of molecules in the far future faces competition from proton decay, if that process proves to be real. If protons are unstable with lifetimes around 10 to the 34th power years, then they will decay long before the quantum tunneling reactions that could form molecules have time to occur. The last chemical reaction might never happen because the atoms needed to participate in it will have already decomposed into lighter particles. The possibility of chemistry in the far future universe raises profound questions about the relationship between complexity and time. Even when the universe appears to have reached maximum entropy and thermal death, quantum mechanics allows for the spontaneous appearance of organized structures through processes that operate on timescales beyond human comprehension. These ultra-rare molecular formation events also suggest that the universe might retain a form of hidden creativity even in its final state, continuously generating new configurations of matter and energy through quantum processes that never cease completely. The far future cosmos becomes like a vast laboratory where nature conducts experiments with infinite patience and unlimited time. Yet, even as molecules might still form through quantum tunneling, the background radiation that has illuminated the universe since its birth approaches its final fade. The cosmic microwave background radiation, the afterglow of the Big Bang that currently bathes the entire universe in faint heat equivalent to negative 454 degrees Fahrenheit, will continue cooling and redshifting until it fades completely into the quantum noise of empty space, erasing the last direct evidence that our universe ever experienced a hot, dense beginning nearly 14 billion years ago. This final dimming represents the universe's transition from a cosmos still warmed by its violent birth to one that has forgotten its own origin story. Currently, the cosmic microwave background provides a nearly uniform bath of photons that fills all of space with radiation corresponding to a blackbody temperature of 2.7 degrees above absolute zero. These photons originated when the universe was only 380,000 years old and had cooled enough for electrons to combine with atomic nuclei for the first time, making space transparent to light and allowing radiation to travel freely across cosmic distances. As space expands under the influence of dark energy, the wavelengths of these ancient photons stretch longer and longer while their energy decreases correspondingly. The radiation that currently appears as microwaves will gradually redshift through radio waves, then to wavelengths measured in meters, kilometers, and eventually astronomical units as the expansion continues accelerating exponentially over cosmic time. The cooling follows a precise mathematical relationship. As the universe doubles in size, the temperature of the background radiation drops by half. Since current observations suggest that cosmic expansion will continue accelerating forever, this cooling process will also continue indefinitely, with the temperature approaching absolute zero asymptotically, but never quite reaching it. In about 1 trillion years, the cosmic microwave background will have cooled to less than 1 degree above absolute zero, making it colder than any temperature ever achieved by human technology. The radiation will have redshifted into the far infrared range, becoming invisible to the types of detectors we use today, but still detectable, in principle, by instruments sensitive to extremely long wavelength electromagnetic radiation. But the cooling continues relentlessly as space keeps expanding. In 10 to the 15th power years, the background temperature will drop below 1,000th of a degree above absolute zero, and the photons will have wavelengths longer than the distance from Earth to the Sun. These ultra-long wavelength photons still carry energy and can still be detected, but they become increasingly difficult to distinguish from other sources of electromagnetic radiation in the universe. Eventually, the cosmic microwave background will redshift so far that individual photons have wavelengths comparable to the size of the observable universe itself. At this point, the radiation becomes fundamentally undetectable because no measurement device could be large enough to span a complete wavelength and determine the photon's properties through standard electromagnetic interactions. The mathematical limit of this cooling process occurs when the background radiation temperature approaches the Planck temperature divided by the age of the universe measured in Planck time units. This gives a final temperature so close to absolute zero that the difference cannot be expressed using ordinary numbers, requiring scientific notation with hundreds of zeros in the denominator. But quantum mechanics prevents the universe from ever reaching exactly absolute zero temperature because of the irreducible zero-point energy that exists in all quantum fields. Even after the cosmic microwave background has redshifted into virtual non-existence, quantum vacuum fluctuations will continue creating virtual photons that pop into existence and disappear again on timescales shorter than the uncertainty principle allows direct observation. These quantum fluctuations set a fundamental lower limit on the temperature of empty space that cannot be reduced no matter how much the universe expands or how much time passes. The final equilibrium temperature will be determined by the balance between the cooling effects of cosmic expansion and the heating effects of quantum vacuum energy, resulting in a temperature infinitesimally close to, but still greater than absolute zero. The fade to black of the cosmic microwave background also erases the last direct observational evidence of the Big Bang and the early universe's hot, dense state. Future observers, if any could exist in the far future cosmos, would have no way to discover that the universe ever experienced a period of rapid expansion and cooling unless they could detect other, more subtle traces of cosmic history preserved in particle correlations or gravitational wave signatures. This represents a profound loss of cosmic memory, as the universe essentially forgets its own birth and early evolution when the background radiation becomes too faint to detect. The smooth, nearly uniform pattern of the cosmic microwave background, which currently provides our best window into conditions during the universe's first few 100,000 years, will disappear into the quantum noise of the vacuum. The fading of the cosmic microwave background also marks the end of the radiation-dominated era of cosmic evolution that began with the Big Bang itself. For nearly 14 billion years, this ancient light has provided a constant reminder that the universe was once very different from its current state, filled with hot, dense matter and energy rather than the cold, empty space that dominates today. But even as this ancient light fades away, the universe continues its expansion toward regions of space that have never been explored. As space continues its accelerating expansion under the influence of dark energy, the universe will eventually grow so large that light from the most distant regions cannot reach us even if it travels for infinite time, creating cosmic horizons beyond which entire galaxies, stars, and civilizations remain forever invisible and unknowable to observers in any particular location. This expansion transforms the universe from a cosmos where everything is potentially observable to one where most of reality lies permanently beyond the reach of scientific investigation. Currently, our observable universe extends to a distance of about 46 billion light-years in all directions, encompassing all the matter and energy whose light has had time to reach us since the Big Bang occurred 13.8 billion years ago. But this observable horizon represents only a tiny fraction of the total universe, which could be infinite in size, and certainly extends far beyond what we can currently detect with our most powerful telescopes. The expansion of space affects observability in counterintuitive ways because space itself grows larger rather than objects moving through fixed space. Galaxies beyond a certain distance recede from us faster than the speed of light, not because they move through space at superluminal velocities, but because the space between us and them expands at superluminal rates. This expansion carries light away from us faster than the light can travel toward us, making those galaxies permanently unreachable. As dark energy continues accelerating the expansion, the boundary of our observable universe will actually shrink rather than grow larger. Galaxies that we can currently see will gradually disappear beyond our cosmic horizon as they get carried away by the expanding space between us and them. The night sky will slowly empty, as distant objects redshift out of visibility and disappear into regions of space that no longer maintain causal contact with our location. In about 150 billion years, all galaxies outside our local gravitational group will have moved beyond our observable horizon, making it appear as though our small cluster of galaxies represents the entire universe. Future astronomers in such a cosmos would have no way to discover that billions of other galaxies once existed within their observable range, because all evidence of those galaxies would have been carried away by cosmic expansion. This cosmic isolation will continue indefinitely as the expansion accelerates exponentially under dark energy's influence. Eventually, even galaxies within our local group will begin to separate as the expansion overcomes their mutual gravitational attraction. Our own galaxy will find itself increasingly alone in an apparently empty universe where no other sources of light remain visible across the growing gulf of expanding space. The mathematics of cosmic horizons show that each observer in the far future universe will be surrounded by a shrinking sphere of observability beyond which no information can ever reach them. This creates a kind of cosmic solitary confinement where each surviving observer becomes trapped within their own causal patch of space-time, unable to communicate with or even detect the existence of observers in other regions. The phenomenon affects not just visual observations, but all forms of information transfer. Gravitational waves, electromagnetic radiation, and even hypothetical faster-than-light signals cannot cross the cosmic horizon once it forms, because the expansion of space itself prevents any causal influence from propagating between widely separated regions. Each observer becomes permanently isolated within their own observable universe. This isolation has profound implications for the concept of cosmic truth and scientific knowledge. If most of the universe lies forever beyond observation, then statements about the total size, content, or properties of the cosmos become meaningless from an empirical standpoint. Science becomes limited to studying only the tiny fraction of reality that remains accessible within each observer's shrinking horizon. The expansion also creates temporal paradoxes about the definition of cosmic simultaneity. Events that appear simultaneous from one observer's perspective could be separated by billions of years from the perspective of an observer in a different causal patch. The concept of universal time becomes meaningless when different regions of space-time lose the ability to synchronize their clocks or share information about when events occur. Some theoretical physicists speculate that the accelerating expansion might eventually become so extreme that it tears apart bound systems like galaxies, solar systems, and even atoms themselves in a scenario called the Big Rip. In this case, the observable universe would shrink to microscopic scales before disappearing entirely, leaving each particle isolated within its own infinitesimal cosmic horizon. But current observations suggest that dark energy has constant density rather than increasing density, which would lead to exponential expansion rather than the super-exponential expansion required for a Big Rip scenario. The universe would continue growing larger forever, while individual observable regions shrink, creating infinite space filled with causally disconnected patches that can never interact or exchange information. This cosmic loneliness represents one of the strangest predictions of modern cosmology, a universe that becomes increasingly empty and isolated as it ages. transforming from a cosmos filled with observable structure and activity to one where each location exists in apparent solitude within an ever-expanding ocean of unreachable space. Yet even within these shrinking bubbles of observability, the fundamental constituents of matter face their own ultimate reckoning. In the unimaginably distant future, roughly 10 to the 34th power years from now, the last proton in the observable universe will spontaneously decay into lighter particles through quantum processes, so rare they make winning the lottery every second for 1 trillion years seem like a certainty. This decay will mark the absolute end of ordinary matter as we know it, converting the final remnant of atoms, molecules, and solid objects into a brief flash of energy that quickly disperses into the ever-expanding emptiness of space. The proton has persevered through every catastrophe in cosmic history, surviving the death of stars, the evaporation of black holes, and the cooling of space to temperatures approaching absolute zero. These positively charged particles have maintained their identity and properties unchanged since the first moments after the Big Bang, when quarks and gluons first combined to form the building blocks of atomic nuclei that would eventually power stars and create the chemical elements necessary for planets and life. But grand unified theories in particle physics predict that protons are not actually immortal, despite their apparent stability over the 13.8 billion years of cosmic history we have observed so far. These theories suggest that protons can decay through incredibly rare quantum tunneling events that convert quarks into leptons, transforming matter into energy according to pathways that violate conservation laws temporarily, while preserving them on average over vast timescales. The predicted proton lifetime ranges from about 10 to the 34th power years to 10 to the 40th power years, depending on which grand unified theory proves correct and what values the fundamental coupling constants take at extremely high energy scales. These lifetimes are so long that they strain human comprehension. If you started with 10 to the 80 power protons, roughly the number in the observable universe today, you would wait 10 to the 34th power years before half of them decayed. When the final proton finally undergoes its quantum death, it will typically decay into a positron and a neutral pion, which immediately decays further into 2 gamma-ray photons. The positron will search through the vast emptiness of space until it eventually encounters one of the few remaining electrons, whereupon both particles will annihilate in a final flash of pure energy that converts their rest mass entirely into electromagnetic radiation. This annihilation will produce 2 photons traveling in opposite directions at the speed of light, carrying away the last traces of the matter that once composed stars, planets, and living beings. These photons will continue propagating through expanding space forever, gradually redshifting to longer and longer wavelengths until they become indistinguishable from the quantum fluctuations of the vacuum itself. The decay process happens randomly for individual protons, following the same statistical laws that govern radioactive decay in unstable atomic nuclei. Most protons will persist far longer than the average lifetime, while a few unlucky ones will decay much sooner through quantum fluctuations that cannot be predicted or prevented by any known physical process. Long before the final proton decays, almost all other protons in the universe will have already undergone their quantum deaths, leaving behind a cosmos filled only with electrons, positrons, neutrinos, and photons scattered across distances so vast that they rarely encounter each other. The final proton will exist in profound isolation, perhaps drifting alone through its own observable universe with no other matter anywhere within causal reach. From the proton's perspective, if we could imagine it having one, the decay will occur without warning, as quantum tunneling suddenly converts its constituent quarks into lighter particles that cannot be confined within the nuclear binding forces. The proton will simply cease to exist, replaced by particles and energy that scatter into space at relativistic velocities. The decay also represents the final victory of quantum mechanics over classical physics in the far future universe. Even the most stable structures that classical physics would expect to persist forever must eventually succumb to quantum processes that operate according to probability rather than certainty, randomness rather than determinism. But the mathematics of proton decay contain profound uncertainties because they depend on physics at energy scales far beyond what we can test directly with particle accelerators. The predicted lifetimes could be wrong by many orders of magnitude, or protons might prove to be absolutely stable against all possible decay processes, in which case they would persist forever as the universe's most enduring survivors. If protons are indeed mortal, their decay will mark the completion of a process that began with the first stellar nuclear reactions, the conversion of matter into energy on cosmic scales. Every star that ever shone, every supernova that ever exploded, and every black hole that ever evaporated contributed to this ultimate transformation of mass into massless radiation and elementary particles. The energy released by proton decay throughout the far future will exceed the total energy produced by nuclear fusion in all stars that ever existed, providing a final burst of cosmic activity during periods when no other energy sources remain available. The universe will glow faintly with the light of proton decay for time periods that make the stellar era seem like a brief moment in cosmic history. When the last proton finally decays, it will end an era that began with the formation of the first atomic nuclei during Big Bang nucleosynthesis, only a few minutes after the universe began. For 10 to the 34th power years, protons will have served as the fundamental building blocks of complexity, enabling the existence of atoms, molecules, planets, and life before finally surrendering to the quantum processes that govern reality at its deepest level. But even after matter itself disappears, the universe may still harbor one final conscious witness to its own ending. In the unimaginably distant future, when the last stars have burned out, the final black holes have evaporated, and even protons begin their ultimate decay into elementary particles, the question of consciousness becomes both profound and paradoxical. Could any form of awareness survive to witness the universe's final transformation? And if so, what would such a consciousness experience as reality itself approaches its ultimate limits? The answer challenges our deepest assumptions about the nature of mind, memory, and existence itself. Traditional biological consciousness faces obvious obstacles in the far future universe. Living organisms depend on chemical processes that require liquid water, stable temperatures, and energy gradients to power metabolic reactions. None of these conditions will exist when the cosmos reaches thermal equilibrium at temperatures approaching absolute zero, making conventional life impossible long before the universe enters its final phases of evolution. But consciousness might not require biological substrates to exist. If awareness is fundamentally about information processing rather than the specific materials that perform the processing, then consciousness could potentially survive by migrating to other physical systems that can manipulate and store information even under the extreme conditions of the far future cosmos. Some theoretical physicists speculate that consciousness could exist as patterns in quantum field fluctuations, using the virtual particle pairs that spontaneously appear in the vacuum as a substrate for information processing and memory storage. Such a consciousness would operate according to principles completely alien to human experience, existing as pure information encoded in the correlations between quantum states scattered across cosmic distances. The energy requirements for consciousness in the far future universe would be incredibly stringent because available energy approaches zero as the cosmos cools toward absolute zero. Any conscious system would need to operate with perfect efficiency, using every quantum of energy for essential information processing while generating no waste heat that could not be recovered and recycled. This leads to what computer scientists call reversible computation, where every computational step can be undone without losing information or generating entropy. Reversible computers can, in principle, perform unlimited amounts of calculation using arbitrarily small amounts of energy, making them the only type of information processing system that could potentially operate in the energy-starved far future universe. But reversible computation faces fundamental limits imposed by quantum mechanics and thermodynamics. The no-cloning theorem prevents quantum information from being copied perfectly, making error correction extremely difficult. Quantum decoherence causes information to leak from quantum systems into their environments, gradually degrading the coherence needed for complex computation. A conscious system in the far future might need to exist in a state of hibernation for vast periods, awakening only when rare quantum fluctuations provide enough energy for brief moments of active thought. The subjective experience of such a consciousness would be radically discontinuous, with thoughts separated by periods of unconsciousness lasting longer than the current age of the universe. The isolation imposed by cosmic expansion would also affect consciousness in the far future. If awareness requires information integration across extended networks, then the accelerating expansion of space could fragment consciousness by carrying its components apart faster than information can travel between them. Each piece of a distributed consciousness would become causally disconnected from the others, potentially creating multiple separate awarenesses from what was once a unified mind. Memory presents another fundamental challenge for far future consciousness. Storing information requires energy to maintain the physical structures that encode memories, and this energy becomes increasingly scarce as the universe cools. A conscious system might need to forget almost everything about its past in order to conserve enough energy to remain aware in the present moment. Yet forgetting creates philosophical puzzles about personal identity and continuity of consciousness. If a conscious system must constantly delete its memories to survive, in what sense does it remain the same consciousness over time? The entity that witnesses the universe's final moments might bear no resemblance to the consciousness that began the journey billions of years earlier. The mathematics of consciousness in the far future universe involves sophisticated calculations from quantum information theory, thermodynamics, and computational complexity theory. The results suggest that awareness might be possible under these extreme conditions, but only in forms so alien to human experience that we lack adequate language to describe them. Such a consciousness would experience time very differently than biological minds, with subjective moments separated by objective eons. As the system waits for quantum fluctuations to provide enough energy for brief bursts of thought, the universe's approach to thermal death would unfold as a series of discrete, discontinuous experiences rather than a smooth, continuous process. The conscious witness to the universe's ending would also face the ultimate existential question. What is the purpose of awareness when nothing can be changed, no goals can be achieved, and no other conscious beings exist to share the experience? Perhaps the mere act of witnessing becomes its own justification, providing the universe with a final observer to record its passage from complexity to simplicity, from structure to emptiness, from existence to whatever comes next. But as this final consciousness contemplates the universe's fate, the heat-death that has dominated cosmic evolution for so long finally completes its inexorable victory. After 10 to the 100th power years of cosmic evolution, the universe finally achieves the state that thermodynamics has been driving it toward since the moment of the Big Bang: perfect thermal equilibrium, where every region of space reaches exactly the same temperature and no energy gradients exist anywhere to power, work, change, or the complex processes that once made stars shine and life possible. This heat death represents the ultimate victory of entropy over order, simplicity over complexity, and eternal stillness over the dynamic evolution that has characterized cosmic history for nearly 14 billion years. The path to heat death has been inexorable since the universe began expanding and cooling, driven by the fundamental laws of thermodynamics that require energy to flow from hot regions to cold regions until all temperature differences disappear. Every star that ever burned, every chemical reaction that ever occurred, and every biological process that ever sustained life contributed to this cosmic leveling by converting useful energy into waste heat that radiates away into space. In the current universe, temperature differences between stellar cores and the cosmic background radiation drive all the processes we observe, from nuclear fusion in stars to the formation of planets and the evolution of life. These temperature gradients provide the free energy that allows complex structures to form and maintain themselves against the disorganizing effects of entropy. But the second law of thermodynamics guarantees that these gradients must eventually disappear. As the universe expanded and cooled over cosmic time, the temperature differences became smaller and smaller. The cosmic microwave background radiation cooled from billions of degrees to its current temperature of -454 degrees Fahrenheit, while stellar cores maintain temperatures of millions of degrees by burning nuclear fuel. But one by one, stars exhausted their fuel and died, eliminating the temperature gradients that had powered cosmic evolution. Black holes temporarily delayed the heat death by concentrating matter and energy into regions with extreme temperature gradients, but Hawking radiation ensured that even these gravitational monsters eventually evaporated completely. The energy released by black hole evaporation spread uniformly through space, contributing to the overall warming of the cosmic background, while eliminating the concentrated energy sources needed for complex processes. The final approach to thermal equilibrium happens gradually as the remaining particles in the universe exchange energy through increasingly rare interactions until their kinetic energies reach perfect balance. Quantum mechanics prevents the temperature from reaching exactly absolute zero, but the final equilibrium temperature will be so close to zero that the difference cannot be measured by any conceivable instrument. At thermal equilibrium, the universe contains maximum entropy and minimum available energy. No work can be performed because work requires energy to flow from high-temperature reservoirs to low-temperature reservoirs, and no such temperature differences exist in a system at thermal equilibrium. The universe becomes like a heat engine with both its hot and cold reservoirs at exactly the same temperature, making it impossible to extract useful work regardless of how clever the engineering might be. The achievement of heat death also represents the completion of a cosmic information processing task that began with the Big Bang. Every physical process in the universe can be viewed as a form of computation that transforms input information into output information according to the laws of physics. The heat death occurs when this cosmic computation reaches its final state, with no further information processing possible because all available energy has been converted into waste heat. The mathematical description of heat death involves statistical mechanics calculations that show how systems with many degrees of freedom inevitably evolve toward states of maximum entropy. The universe contains approximately 10 to the 80 power particles, creating a system with so many degrees of freedom that its approach to thermal equilibrium becomes virtually certain over cosmic time scales. But heat death is not the same as the cessation of all activity. Even at thermal equilibrium, quantum fluctuations continue to create temporary departures from perfect balance, causing virtual particles to appear and disappear in the vacuum, and occasionally giving real particles slightly more or less energy than the average. These fluctuations represent the universe's final form of activity, a quantum mechanical metabolism that persists even when all macroscopic processes have ceased. The heat death also preserves all information about the universe's history in the quantum correlations between particles and the detailed patterns of electromagnetic radiation filling space. This information remains perfectly accessible in principle, but extracting it would require more energy than the universe contains, making it practically inaccessible while remaining theoretically present. Some cosmologists speculate that heat death might not represent the absolute end of cosmic evolution, because quantum fluctuations could occasionally create departures from thermal equilibrium large enough to restart processes of structure, formation, and complexity generation. These fluctuations would be extraordinarily rare, but given infinite time, even processes with infinitesimal probabilities must eventually occur. The heat death of the universe also raises profound questions about the arrow of time and the nature of causality. In a system at thermal equilibrium, the distinction between past and future becomes meaningless because no irreversible processes occur to define a preferred temporal direction. Time continues to exist as a mathematical parameter, but it loses its physical significance as a measure of change and evolution. Yet even in this state of perfect thermal equilibrium, the universe retains one final surprise that could potentially transform everything we understand about the nature of reality. In the ultimate far future, when protons have decayed, black holes have evaporated, and even the last photons have redshifted into virtual non-existence, The universe will be dominated by quantum foam, a seething microscopic texture of space-time itself, where virtual particles and antiparticles constantly appear and disappear on scales smaller than atomic nuclei, creating the only remaining form of activity in a cosmos that has otherwise achieved perfect stillness and thermal death. Quantum foam arises from the fundamental uncertainty principle, which prevents space-time from being perfectly smooth even at the smallest possible scales. Just as quantum mechanics forbids particles from having precisely defined positions and velocities simultaneously, it also prevents the geometry of space itself from being exactly flat and motionless. The fabric of reality constantly fluctuates, with tiny distortions that create and destroy virtual particle pairs faster than the uncertainty principle allows direct observation. These fluctuations operate on the Planck scale, involving distances of approximately 10 to the negative 35th power meters and time intervals of 10 to the negative 44th power seconds. At such scales, the familiar concepts of space and time begin to break down, replaced by a probabilistic foam where cause and effect become blurred, and the distinction between matter and empty space loses its meaning. In the current universe, quantum foam is completely overwhelmed by much larger scale phenomena like electromagnetic radiation, gravitational fields, and the motion of particles through space. The foam exists everywhere, but its effects are so subtle that they can only be detected through extremely sophisticated experiments that probe the fundamental limits of measurement imposed by quantum mechanics and relativity. But in the far future universe, when all other forms of matter and energy have dissipated or decayed, quantum foam becomes the dominant feature of reality. The vacuum itself becomes a dynamic, ever-changing medium where virtual photons, electrons, quarks, and other particles briefly materialize before vanishing back into nothingness. This process continues indefinitely because it represents an irreducible property of quantum fields rather than a temporary phenomenon that could eventually cease. The energy associated with quantum foam is enormous when calculated naively, suggesting that every cubic inch of empty space contains more energy than all the matter in the observable universe. This leads to what physicists call the vacuum energy problem, or cosmological constant problem, one of the most serious unsolved puzzles in theoretical physics. Something must cancel out most of this vacuum energy, but we do not understand what or how. Despite this theoretical difficulty, quantum foam produces observable effects that confirm its reality. The Casimir effect demonstrates that quantum fluctuations in the vacuum can generate measurable forces between closely spaced metal plates by slightly altering the spectrum of virtual particles that can exist in the confined space between them. This proves that the vacuum is not empty, but filled with quantum activity. In the far future universe, quantum foam will create a kind of cosmic weather system operating on microscopic scales, with virtual particle storms briefly illuminating tiny regions of space before dissipating back into the vacuum. These events will be the only things happening anywhere in the cosmos, the final remnant of the dynamic processes that once powered stars, galaxies, and life itself. The foam also provides the mechanism by which the universe could potentially escape from thermal death through extraordinarily rare but not impossible quantum fluctuations that create pockets of low entropy within the overall high entropy environment. These fluctuations could spontaneously generate organized structures like atoms, molecules, or even more complex systems through pure chance operating over infinite timescales. The mathematics describing quantum foam involves advanced techniques from quantum field theory and general relativity that push the boundaries of current theoretical physics. The calculations require summing over all possible virtual particle interactions in curved space-time, a task so complex that physicists have developed entire mathematical frameworks just to handle the infinite series that arise in these computations. Quantum foam also raises deep questions about the nature of reality at its most fundamental level. If space-time itself is constantly fluctuating and changing on microscopic scales, then what we perceive as solid, stable reality emerges as a statistical average over countless quantum events that individually follow no deterministic laws. Reality becomes probabilistic rather than certain, process-based, rather than substance-based. The foam connects to speculative theories about the multiverse and the possibility that our entire universe might be just one bubble in an infinite sea of quantum foam that occasionally creates regions of space-time with different physical laws and constants. Each bubble would represent a separate universe with its own history and evolution, most of which would remain forever inaccessible to observation from any other bubble. In the context of the far future, quantum foam ensures that the universe never becomes completely static or perfectly empty. Even when all matter has decayed and all energy has dissipated, the foam continues its microscopic dance of creation and destruction, maintaining a minimal level of activity that persists as long as quantum mechanics and space-time itself exist. The virtual particles in quantum foam also carry information about the universe's history encoded in their quantum correlations and statistical properties. This information becomes the final repository of everything that ever happened in cosmic history, preserved in a form that transcends the destruction of all material records, but remains forever locked away by the fundamental limits of quantum measurement. Yet, even as quantum foam replaces all matter as the universe's primary constituent, the cosmos itself might be preparing for one final, impossible transformation. Deep within the quantum foam that dominates the far future universe lurks a possibility so extraordinary it defies human comprehension. The spontaneous creation of entirely new universes through quantum fluctuations so rare, they would typically require waiting periods longer than 10 to the 10 to the 10 to the 56 power years. Yet given infinite time, such events become not just possible but inevitable. These quantum births could restart cosmic evolution from absolute nothingness, creating new Big Bangs that begin fresh cycles of stellar formation, galaxy evolution, and perhaps even life itself. The process begins with what physicists call a false vacuum fluctuation, where quantum uncertainty temporarily creates a microscopic bubble of space-time with different physical properties than the surrounding vacuum. Most such fluctuations collapse immediately back into nothingness, but extremely rare fluctuations can become self-sustaining and begin expanding at exponential rates, effectively creating new universes within the quantum foam of the old one. Think of it as the ultimate example of something arising from nothing, except that nothing in quantum mechanics is never truly empty, but filled with the irreducible activity of virtual particles and field fluctuations that cannot be eliminated even in perfect vacuum. The quantum vacuum retains enough energy and uncertainty to occasionally create macroscopic structures through processes that have no classical analog. The mathematics describing universe creation from quantum fluctuations involves concepts from inflation theory, quantum tunneling, and statistical mechanics that operate at the intersection of gravity, quantum mechanics, and thermodynamics. The calculations suggest that given sufficient time, quantum fluctuations will eventually create fluctuations large enough and persistent enough to evolve into expanding regions of space-time with their own distinct physical laws. These new universes would initially be microscopic, perhaps smaller than atomic nuclei, but they would contain within themselves the potential for exponential expansion through inflationary processes similar to those that shaped our own universe during its first tiny fraction of a second after the Big Bang. The expanding bubble would quickly grow larger than its parent universe, while remaining completely disconnected from it causally. The probability of such spontaneous universe creation is so astronomically small that it makes proton decay look like a frequent occurrence. Current estimates suggest typical waiting times of 10 to the 10 to the 56 power years or longer, time periods so vast that they cannot be expressed using ordinary mathematical notation and require specialized techniques from number theory just to write them down. But infinity is longer than any finite number, no matter how large. Given unlimited time, processes with arbitrarily small probabilities must eventually occur through the random fluctuations of quantum mechanics. The far future universe has unlimited time available for these ultimate rare events to manifest themselves through sheer statistical inevitability. Each new universe created through quantum fluctuation would begin with its own Big Bang and evolve according to its own set of physical constants and laws. Some might have stronger or weaker fundamental forces, different numbers of spatial dimensions, or physical constants that prevent the formation of atoms, stars, or complex structures. Others might create conditions even more favorable to complexity in life than our own universe provides. The new universes would remain forever inaccessible to observation from the parent universe because they expand within their own space-time that has no causal connection to the surrounding quantum foam. They would exist as completely separate realities, each unaware of the others and unable to exchange matter, energy, or information across the boundaries that separate different space-time manifolds. This process could continue indefinitely, with each new universe eventually reaching its own heat death and spawning additional universes through its own quantum fluctuations. The result would be an infinite hierarchy of universes, creating universes, each generation completely isolated from all the others but connected through their common origin in the quantum mechanical properties of the vacuum. The concept of universe creation from nothing also provides a potential resolution to the ultimate fate of our own cosmos. Even if our universe reaches perfect thermal equilibrium and remains in that state for periods exceeding human comprehension, quantum fluctuations ensure that new regions of low entropy will eventually appear, potentially restarting processes of cosmic evolution within the dead universe. Some theoretical physicists speculate that consciousness itself might play a role in universe creation through what they call the participatory anthropic principle, where the act of observation by conscious beings influences the probability of quantum events that could lead to universe formation. In this view, consciousness becomes a cosmological force that helps ensure the continued creation of universes capable of supporting life and awareness. The spontaneous creation of universes from quantum fluctuations also raises profound philosophical questions about the nature of existence, causality, and the relationship between being and non-being. If entire universes can arise from nothing through pure chance, then the distinction between existence and non-existence becomes blurred at the deepest level of reality. But even as we contemplate these ultimate possibilities for cosmic renewal, one final question remains that may determine whether any of this speculation has meaning. As our journey through deep time reaches its conclusion, we arrive at the most profound mystery in all of physics. What happens to reality itself when the universe has exhausted every possible source of change, consumed every gradient of energy, and approached as close to absolute zero as quantum mechanics allows? The answer to this ultimate question may determine whether the cosmos faces true eternal death or holds within itself the seeds of infinite renewal, forever cycling between existence and void in patterns too vast for any mind to fully comprehend. Absolute zero represents more than just the coldest possible temperature. It embodies the thermodynamic limit, where all classical motion ceases and systems reach their lowest possible energy states. Yet quantum mechanics ensures that even at absolute zero, the universe retains irreducible zero-point energy that manifests as persistent fluctuations in all quantum fields. These fluctuations suggest that perfect stillness is impossible, that reality at its deepest level remains eternally active even when all macroscopic processes have ceased. The approach to absolute zero forces us to confront the fundamental question of whether the universe is finite or infinite in its ultimate scope. If space and time are finite, then the cosmos will eventually reach a state of perfect thermal equilibrium where nothing further can happen, creating a static eternity of quantum fluctuations without larger meaning or purpose. But if the universe is infinite, then rare quantum events will continue occurring forever, occasionally creating pockets of low entropy that could restart processes of cosmic evolution. The mathematics of infinity suggests that even events with infinitesimally small probabilities must occur infinitely often given unlimited time and space. This means that quantum fluctuations could spontaneously create new Big Bangs, new regions of space-time with different physical laws, and new opportunities for the emergence of complexity, structure, and perhaps consciousness itself. The universe becomes eternally creative, forever generating new realities from the quantum foam of apparent nothingness. But infinity also creates paradoxes that challenge our understanding of causality, probability, and existence itself. If everything that can happen must happen infinitely often, then every possible universe, every possible conscious experience, and every possible story plays out countless times across the infinite expanse of space and time. The heat death of our particular cosmic patch becomes merely one episode in an infinite drama of creation and destruction. The approach to absolute zero also raises questions about the nature of time itself in the far future universe. When no changes occur and no processes mark the passage of temporal duration, does time continue to exist as a meaningful concept? Or does the cosmos transition into a timeless state where past, present, and future lose their distinction and reality becomes a static, four-dimensional block where all events exist simultaneously? Some physicists speculate that absolute zero represents not an ending but a phase transition, like water freezing into ice or gas condensing into liquid. The universe might undergo a fundamental change in its basic structure and properties when it reaches maximum entropy, transforming into something so alien that our current concepts of space, time, matter, and energy no longer apply. The quantum foam that dominates the far future universe retains within itself all the information that ever existed in cosmic history, encoded in correlations between virtual particles and field fluctuations that persist even when all matter has decayed. This information could potentially serve as the blueprint for cosmic renewal, providing the pattern from which new universes could emerge through rare quantum fluctuations. The ultimate question also connects to the deepest mysteries of consciousness and existence. If awareness is truly fundamental to reality, rather than an emergent property of complex matter, then consciousness might persist even beyond absolute zero, experiencing the universe's final transformation and perhaps playing a role in determining what comes next. The final witness to cosmic death might also be the agent of cosmic rebirth. Recent discoveries in theoretical physics suggest that our universe might exist within a vast landscape of possible realities, each characterized by different values of the fundamental constants and physical laws. The approach to absolute zero in our cosmos might represent just one thread in an infinite tapestry of universes, each following its own trajectory toward heat death while contributing to the overall evolution of the multiverse. The question of what comes after absolute zero ultimately forces us to confront the limits of scientific knowledge itself. We are asking about conditions so extreme and timescales so vast that they may forever lie beyond the reach of experimental verification or direct observation. The answer becomes as much a matter of philosophy and imagination as empirical science. Yet the question compels us because it represents the ultimate test of our understanding of reality. If we can comprehend what happens when the universe reaches its absolute limits, then perhaps we have truly grasped the fundamental nature of existence itself. The journey from the Big Bang to absolute zero becomes humanity's greatest intellectual adventure. Our species' attempt to understand our cosmic origins, our ultimate destiny, and our place in the vast scheme of existence. As we stand at the threshold of this ultimate mystery, gazing forward through deep time toward the universe's final moments, we realize that the question of what comes after absolute zero is really asking what comes after everything we know, everything we can imagine, and everything we thought was possible. The answer may be nothing, or it may be everything, or it may be something so far beyond our current understanding that we lack even the concepts needed to think about it properly. The final proton, drifting alone through space colder than imagination, approaches its quantum death in a universe that has forgotten its own birth. What witnesses this ending? What comes next? The ultimate question remains, waiting for an answer that may itself transcend the very notion of answers, carrying us beyond the boundaries of knowledge into realms where science, philosophy, and wonder become indistinguishable from each other. In the end, perhaps the question itself is the answer. The universe's greatest achievement may not be the stars it created, the life it nurtured, or the consciousness it awakened, but the questions it inspired in minds capable of contemplating their own cosmic significance. The journey from the first moment to the last may be less important than the awareness that made the journey meaningful, the consciousness that could witness time itself prepare to die.